Hello there, and welcome to Science for Sleep, where the wonders of the cosmos settle into a quieter rhythm and curiosity drifts gently alongside rest. Tonight, I'd like to invite you to lean back, breathe a little slower, and let your thoughts soften as we take a journey into something that feels almost impossible to imagine, something so immense that even our best numbers strain to capture it. The question is a simple one on the surface, yet the answers stretch beyond ordinary comprehension. How powerful is the biggest star in the universe? It's a fitting question for a moment like this. You sitting wherever you are in the world right now, with your own sky stretched above you, and me speaking softly into your headphones or speakers, and between us, the idea that out there, scattered across the dark, there exist stars so vast they make our own sun look small and modest. Before we go any further, I'd love to know where you're listening from tonight. Are you somewhere where the stars are visible, maybe faint against the glow of city lights, or brilliantly clear in a quiet countryside sky? Or perhaps it's daytime for you, and the stars are hidden behind the blue. Either way, they're still out there, still burning, still unfolding their immense stories, regardless of whether we notice them or not. If you find these quiet explorations soothing, or if the thought of drifting through space and science helps you ease into sleep, I'd be grateful if you considered giving this little corner of calm a like, or maybe subscribing. It helps this cozy space reach others who might need a pause, a break, or a soft voice in the background. But let's not linger too long on housekeeping. The sky above us is waiting, and it's vast. Imagine for a moment that you're holding a globe in your hands, the kind you might have spun as a child. You turn it, the continents drift past under your fingers, and you trace the oceans. Now imagine trying to fit something onto that globe that is so large it could swallow the globe itself thousands upon thousands of times. That is the scale we're dealing with when we begin to talk about the larger stars. The sun we depend on each day is already 1,000,000 times larger than Earth by volume. Yet compared to the most colossal stars discovered, it is hardly more than a flickering spark. There is something humbling about that. You woke up this morning under the light of the sun, a star powerful enough to grow your food, to drive winds and seasons, to power every living thing you know, and yet somewhere far away, there are stars whose sheer size makes the sun look ordinary. It raises a question that is as simple as it is staggering. If our modest sun can already power all of life, what sort of unimaginable energy is contained in the universe's biggest stars? Part of the difficulty in answering lies in just how alien those giants are. Their surfaces swell outward to such enormous scales that even the words we use, millions, billions, trillions, begin to lose their grip. And still, astronomers have found ways to measure, to compare, to place them onto charts and diagrams that can at least give us a hint of their power. Stars like uyscuti, one of the largest known, stretch to radii so vast that if you placed it where our sun is, its outer layers would reach past the orbit of Jupiter. Think about that for a moment. The sun warms Earth from 150 million kilometers away. Uyscuti would engulf Mercury, Venus, Earth, Mars, and even stretch beyond the asteroid belt. Our whole planetary neighbourhood would be inside its bloated atmosphere. Of course, that picture is not meant to alarm or frighten, only to stretch the imagination. Uyscuti is not near us. It is over 9,000 light-years away, far enough that its story plays out at a comfortable distance. Still, the scale matters because it tells us something about the kind of power we are dealing with. When a star is that large, its energy output is not just higher by a factor of 2 or 3, but sometimes by millions. Every second, it releases more energy than our sun produces in an entire lifetime. But let's take a slower approach. It's tempting to leap right into numbers so large they feel absurd, but I think it's more calming and more meaningful to build up gradually. Think first of a campfire. You know what it feels like to sit by one. You feel its warmth against your skin. The fire consumes wood, turns it into heat and light, and eventually dies out. a star is not so different in principle. It burns fuel, hydrogen primarily, fusing atoms together in its core, and the result of that fusion is light, heat and energy streaming outward. The difference is simply scale. Where a campfire might burn logs, a star burns hundreds of millions of tons of hydrogen every single second. And the larger stars burn through their fuel at an even more ferocious rate, turning unimaginable masses of hydrogen into helium and heavier elements with each tick of time. Astronomers describe this power in terms of luminosity, the total amount of energy a star emits per second. Our Sun has a luminosity defined as one solar unit, a baseline. Some of the larger stars have luminosities not of 2 or 3, but hundreds of thousands, or even millions of times the Sun's. To stand beneath such a star, if it were possible, would be like standing near a fire so bright that it would blind you instantly and sear you from existence. Yet from Earth, even the brightest hypergiants appear as faint specks in the night, their distance softening their glare into the same gentle pinprick as every other star. It's a strange paradox, that something so powerful can seem so small, reduced by distance into a twinkle. That twinkle, though, is enough for astronomers to decode secrets. With careful observation, they can measure how a star's light stretches and shifts, revealing its temperature, its size, and its distance. They can tell how much matter is being expelled in stellar winds, which in the case of the larger stars can be equivalent to losing an entire Earth's worth of material every year. Imagine a star so restless, so powerful, that it sheds mass as if it were brushing dust from its surface, except that dust is billions of tons of plasma rushing out into space at thousands of kilometers per second. And still, even with all that violence, there is a kind of order. The biggest stars are not random explosions of light. They are structured, layered, governed by the balance of gravity pulling inward and fusion pushing outward. That balance is fragile, and the larger the star, the more precarious it becomes, which is why the most massive stars live fast and die young, burning through their fuel in only a few million years. By comparison, our Sun, steady and modest, will last for about 10 billion years. In the language of stars, the giants are like fireworks, brilliant, powerful, but fleeting. Yet for all their brevity, their influence echoes across the universe. When a giant star releases its energy, when it sheds material into space, when it finally explodes in a supernova, the elements forged in its heart scatter outward. Iron, carbon, oxygen, things that will later become planets, oceans, and living beings, are the gifts of those colossal lives. In that sense, the power of the bigger stars is not just about brightness or size, it is about creation. Their power seeds the galaxies with the raw ingredients for life. Without them, we would not be here at all. Even knowing this, even holding the numbers and the science in mind, there's still something almost playful about asking how powerful the biggest star really is. Because no matter how many statistics we list, no matter how precise the data, our minds are not wired to grasp scales so vast. We are creatures of Earth, built to see mountains as large, oceans as immense, and the sun as overwhelming. The leap from that to a star that dwarfs our sun thousands of times over is one that requires not just mathematics, but imagination. And maybe that's the best way to approach it, not as a riddle to solve perfectly, but as an invitation to stretch, to wonder, to let the sheer scale carry us. So here we are, with the question still open before us. We've greeted the sky, we've placed ourselves gently into its enormity, and we've brushed against the edges of what a star can be when it grows to its largest possible size. And now, slowly, quietly, we can begin to wander deeper into the details of what makes such stars expand to such proportions, what sets them apart from the smaller, steadier stars like our own sun, and what kind of lives they lead in the short, fiery spans of their existence. When you tilt your head back and look at the night sky, most of the tiny points you see are stars like our sun, give or take a little in size and brightness. They are familiar, steady, and for the most part modest. The sky, as it presents itself to the human eye, is an even field of dots, some brighter, some fainter, some arranged into constellations we recognise, but all appearing within the same narrow range. It's only when you peer closer, when astronomers gather the faint light in telescopes and measure it carefully, that the illusion begins to unravel. Because hidden in that soft scattering of lights are stars that are not just a little bigger or a little brighter, but so enormous they hardly belong to the same category as our sun. We call them giants, supergiants, and hypergiants. The very words strain to keep up with reality, as if human language had to keep adding syllables in a scramble to describe their size. These are the cosmic behemoths, the sparks in the dark that tip the scales of the universe. They are rare, they are unstable, and they live in ways our sun never could. But they are also, in a very real sense, the engines of creation, scattering elements, sculpting galaxies, and reminding us just how varied stars can be. To begin to imagine one, it helps to think of our sun as a standard measure. The sun is, by definition, one solar mass, one solar radius, and one solar luminosity. We use it as a yardstick. If another star is 2 times the sun's radius, it is twice as wide. If it is 100 times more luminous, it shines 100 times brighter. But when we step into the realm of the giants, these neat multiples explode into extremes. Some giants swell to more than 1,000 times the sun's radius. Picture placing a star like that in the middle of our solar system. Its edge would engulf all the inner planets, sweep past Mars, and threaten to swallow even Jupiter. A familiar neighbourhood suddenly looks like a fragile ornament tucked inside a single swollen star. And yet these giants are not just about size. They are about energy, about lifespans measured not in the steady billions of years like our sun, but in millions, sometimes even less. Their fuel consumption is astonishing. A giant burns through its hydrogen and helium at such a rate that it can exhaust itself in a blink of cosmic time. It's the ultimate contrast. Immense in size, but fleeting in life. If you trace the life of a giant star back to its beginning, you find something familiar. Every star begins in a cloud of gas and dust, a nebula drifting quietly in space. Gravity gathers material, draws it inward, squeezes until the core grows hot enough for fusion to begin. For a smaller star, the process is gradual, restrained. For a giant, it is explosive, fast, and forceful. The newborn giant blazes almost immediately, its mass so great that its core temperature soars, and fusion ignites with fury. From the very first moments of life, a giant star is already on a trajectory that will burn too hot and too fast. Some of the most famous examples carry names that sound almost mythical. Betelgeuse, the bright shoulder of Orion, a red supergiant visible even to the naked eye. Rigel, another star in Orion, luminous enough to be seen from hundreds of light years away. Antares, the heart of Scorpius, glowing with a reddish hue in the summer sky. Each of these is a giant, dwarfing our sun not just in size, but in presence. Their light reaches us across vast gulfs of space, and yet it remains strong enough to be a part of our constellations. That alone tells you something of their power. But as enormous as these familiar giants are, they are not the upper limit. The hypergiants push the boundary further still. Stars like VY Canis Majoris or uyscuti belong to this rare class, with radii thousands of times that of the Sun. They are unstable, often losing mass in colossal stellar winds, their atmospheres puffed out and trembling, as if the star itself is struggling to hold together. Looking at one through a telescope is not like looking at the sharp disk of the Sun. Instead, you see a blurry, extended halo of gas and dust, a star that is literally spilling itself into space. To put such a star into perspective, Imagine the sun as the size of a small coin resting in your hand. On that same scale, a hypergiant would be a sphere as large as a house, glowing, trembling, burning through its existence, and yet the density is surprisingly low. Many hypergiants are so distended that their outer layers are tenuous, less dense than air. If you could somehow stand in that atmosphere, not that it would be survivable, you could drift as if through a thin gas, the star itself so bloated that it is almost ghostly. The paradox is striking. A star that is both immense and fragile, both overwhelmingly powerful and precariously unstable. The giants of the cosmos also redefine brightness. Luminosity is not just a matter of size, but of surface temperature. A hot star radiates more fiercely than a cool one, even if it is smaller. Many blue supergiants shine tens of thousands of times brighter than the sun, their light pouring out across interstellar space. They are visible from such distances that astronomers can use them to trace the arms of galaxies. Without them, some of the grand spirals we photograph would remain invisible, their structure hidden. These stars act like cosmic beacons, marking the edges and patterns of the universe. It is worth remembering how rare they are. For every giant, there are millions of smaller stars like the Sun, or smaller still, the red dwarfs. The giants make up only a tiny fraction of stellar populations. They are the exception, not the rule. But in their rarity lies their significance. They are the ones that go out in spectacular deaths, scattering elements, driving shock waves, and shaping the galaxies around them. Without the giants, the universe would be quieter, simpler, and perhaps lifeless. Their rarity also makes them precious to astronomers. Studying a giant is like studying a rare specimen in nature, one that cannot be found everywhere, one that offers clues about extremes. The physics inside them is pushed to limits, pressures, temperatures, and densities that test our theories. Each observation of a giant star becomes a kind of laboratory experiment, a way to see how matter behaves under conditions we cannot reproduce on Earth. Think, for example, of the pulsations that ripple through some giants. Their outer layers swell and contract rhythmically, making the star brighten and dim in cycles that can last months or years. These variations are not just curiosities. They tell us about the star's internal structure, about how energy moves from the core to the surface, about how matter behaves when stretched across such scales. To watch a star breathe in and out across years is to glimpse processes that are otherwise hidden. And then there are the stellar winds. Ordinary stars like the Sun emit a solar wind, a stream of charged particles that flows outward in all directions. For giants, these winds become tempests, carrying away mass at astonishing rates. Over time, a giant can shed enough material to alter its evolution, to reshape its own destiny. The space around some giants is filled with shells and arcs of ejected gas, like smoke rings drifting outward from a colossal fire. Through infrared telescopes, these shells glow, marking the history of the star's restless shedding. All of this raises a quiet but profound thought. Somewhere, right now, in the galaxy, there is a giant star living out its short, brilliant life. Its light has been travelling toward us for centuries, perhaps millennia, and when it arrives, we see only a twinkle in the night. But if that star were to suddenly collapse and explode in a supernova, its brightness could rival the full moon, casting shadows on Earth even at midnight. Entire civilizations in the past have recorded such events. Stars that suddenly appeared in the sky, brighter than any planet visible in daylight. They were witnessing the death throes of giants. And long after the light faded, the elements forged in that explosion continued their journey, drifting through space, waiting to become part of something new. The giants of the cosmos are not gentle companions like our sun. They are dramatic, unstable, prone to extremes. Yet they are also necessary. Without them, galaxies would be less dynamic, less enriched, less capable of producing the complexity needed for life. In their violence, they create. In their brief lives, they leave legacies that last billions of years. And so, when we speak of the biggest star in the universe, we are not just asking about numbers. We are asking about a class of stars that defy scale, that stand apart from the ordinary, that push physics to its boundaries. They are sparks in the dark, but sparks so immense they illuminate the very structure of the cosmos. To follow their stories is to glimpse the grandest expressions of what a star can be. When we use the word big, it usually feels straightforward. A big tree is taller than the one beside it. A big mountain looms above the valley below. A big wave is the one that rises higher than the rest. But when we talk about stars, big begins to splinter into meanings that are not so simple, because a star can be big in different ways. It can be swollen and wide, stretching across space with a radius 1,000 times that of the Sun. Or it can be dense with mass, packing dozens or even hundreds of solar masses into a volume not much larger than our Sun. Or it can be powerful in its light, shining millions of times brighter, blazing so intensely that entire regions of space are shaped by its radiation. Each of these measures, size, mass, brightness, gives us a different picture of what it means to be big. Take radius, for example. This is often the first image that comes to mind when someone asks about the largest star. How wide is it? How far does its surface extend from its centre? If you place a hypergiant star where our Sun is now, how far out would its edges swell? Uyscuti, often mentioned as a contender for the largest star by radius, would stretch beyond the orbit of Jupiter. That means every planet we know, every moon, every asteroid that orbits inside that boundary would be swallowed inside the star itself. This makes uyscuti enormous in terms of sheer volume. You could fit billions of suns inside it if you used volume as your metric. Yet here's the twist. Despite its massive radius, uyscuti does not carry the most mass. It is swollen, puffed out, extended, but its outer layers are thin, fragile, almost airy compared to denser stars. So in terms of mass, it is not the biggest. Mass tells a different story. The most massive stars discovered are not necessarily the widest. Instead, they are compact compared to their swollen cousins, but their cores are heavy with matter. Take a star like R136A1, found in the Tarantula Nebula. It is one of the most massive known, estimated at over 200 times the mass of the Sun. Yet it is not nearly as wide as uyscuti. It does not stretch across half a solar system, but if you placed it on a scale, so to speak, its gravity would far outweigh the bloated hypergiant. Its mass makes it powerful in ways a swollen star cannot match. Its core burns hotter, its fusion more intense, and its lifespan even shorter. It is like comparing a balloon to a stone. The balloon may take up more space, but the stone carries more weight. Brightness, or luminosity, is yet another angle. Some stars radiate with such intensity that they outshine millions of suns. Rigel, the blue supergiant in Orion, is about 120,000 times more luminous than our Sun. Eta Carinae, a massive stellar system prone to eruptions, shines with several million times the Sun's light. These stars may not have the largest radius or the most mass, but in terms of energy output they are staggering. Imagine holding a candle beside a lighthouse. The candle glows warmly enough to illuminate your hand. The lighthouse beam sweeps across oceans. That is the difference between our Sun and the most luminous stars. So when someone asks what is the biggest star, the answer has to begin with another question. Biggest in what sense? If you mean widest, the bloated red hypergiants take the crown. If you mean heaviest, the compact blue giants and rare monsters like R136A1 win. If you mean most powerful in light, the luminous blue variables and supergiants shine above the rest. Each answer is true, but each paints a different kind of bigness. This multiplicity is not just a trick of language. It reflects something profound about the way stars live. Their size, mass, and brightness are not fixed independently. They are interconnected. A star's mass largely determines its fate. With more mass, gravity presses harder, fusion burns hotter, and the star evolves faster. But as it grows, it may swell outward, increasing its radius while shedding mass in winds. Later, as its fuel runs low, it might contract, becoming smaller in radius but denser and heavier at the core. To speak of size is to speak of a moment in the star's life, a snapshot. But the star itself is changing constantly. Consider Betelgeuse. It is a red supergiant nearing the end of its life. Right now, it is enormous in radius, about 1,000 times wider than the Sun. If placed in our solar system, its surface would nearly reach Jupiter's orbit. But its mass is only about 15 to 20 times that of the Sun. That means it has inflated dramatically, stretching its outer layers thin. It looks gigantic, but its true heft is not as extreme as its size suggests. Contrast that with a young blue giant, perhaps 50 times the Sun's mass. It is not nearly as wide, perhaps only a few tens of times the Sun's radius, but its density and weight make it vastly more powerful in terms of fusion and brightness. This distinction also explains why the term biggest star often sparks debate among astronomers. Different researchers focus on different measures, and depending on what you value, volume, weight, or light, you may crown a different champion. To the public, it can be confusing. One headline announces uyscuti as the largest star, another declares R136A1 as the most massive, another points to Eta Carinae as the brightest. All are true in their way, but they are describing different aspects of stellar grandeur. It helps to compare with something more familiar. Imagine you're asked, what is the biggest animal on Earth? Do you choose the blue whale, the heaviest and longest living animal today, or do you consider the tallest, like the giraffe, or the one with the widest wingspan, like the wandering albatross? Each measure gives a different answer, but all fall under the same question. With stars, the differences are even more dramatic because their scales vary by factors of millions. Even the way we measure these properties adds complexity. Size is estimated by observing how much light the star emits, and combining that with its temperature. Mass is often deduced from the way the star pulls on companions in binary systems, or from the physics of how bright a star of a given mass should be. Luminosity is calculated from distance and brightness, corrected for any dust that dims the light. None of these are direct measurements. They are careful inferences built on physics and observation, which means our estimates carry uncertainties. A star we think of as the largest today may be surpassed tomorrow when new observations refine the numbers. And yet, even with uncertainty, the broad picture is clear. There are stars out there that stretch wider than our entire planetary system. There are stars whose gravity outweighs hundreds of suns. There are stars whose brilliance pierces galaxies. They are big in ways that defy singular description. What makes this especially fascinating is how different these stars appear in the night sky. Some, like Betelgeuse, are visible with the naked eye. You can step outside, look up at Orion, and see the red glow of a dying supergiant. Others, like uyscuti or 136A1, are invisible to the naked eye, buried in distant regions of the galaxy, requiring telescopes to detect. Their light takes thousands of years to reach us, and when it does, it arrives as just another twinkle, indistinguishable from stars far less powerful. The true scale is hidden until science unravels it, and once you do know, the sky changes. That faint dot you never noticed before may be a hypergiant, larger than you can imagine. That bright star you thought ordinary may be a powerhouse tens of thousands of times more luminous than the sun. The night becomes layered with meaning. Behind each point of light lies a story of scale. So when we ask what makes a star big, the answer is not just scientific. It is also about perspective. From Earth, every star looks small. They are all pinpoints, no matter how massive, no matter how wide, no matter how bright. Distance shrinks them to dots. Only when we calculate, compare and imagine do their true sizes emerge. It is a reminder that our senses are limited. To grasp the grandeur of the universe, we need more than sight. We need the patient work of measurement, the quiet act of scaling up from the familiar to the unimaginable. And with that understanding, we can begin to look more closely at individual stars. We can take the giants by name, uyscuti, R136a1, V1 Canis Majoris, and explore not just their numbers but their natures. Because each giant is not just big in abstract terms, but a living star with its own quirks, its own story, its own place in the cosmos. And among them, some stand as symbols of extremity, outliers that show us just how far the universe can stretch the concept of a star. If you were to ask astronomers today which single star deserves the crown for sheer size, the name that often comes up is uyscuti. It is not the brightest star in our sky. It is not even visible to the naked eye. If you stepped outside right now and looked up, you would never pick it out. But hidden in the constellation of Scutum, some 9,500 light-years from Earth, this red hypergiant sits quietly as one of the largest stars ever measured. It is the kind of star that makes the imagination stumble, because every number attached to it feels absurd, even when those numbers are grounded in careful science. The first thing to know about uyscuti is that it is not some brand new discovery. It was catalogued in the 19th century, originally marked simply as another variable star in the crowded region near the centre of our Milky Way. The name itself, uyscuti, follows the standard convention for variable stars. Letters assigned in order of discovery, followed by the name of the constellation. In that sense, the name is unremarkable, almost plain. But behind the plain designation lies something extraordinary. Astronomers estimate that uyscuti has a radius around 1,700 times that of our Sun, though because of the way its outer atmosphere swells and contracts, the exact number wavers. Even on the low end of the range, it remains staggering. If you were to place uyscuti in the centre of our solar system where the Sun is now, its outer layers would stretch well beyond the orbit of Jupiter. Mercury, Venus, Earth and Mars would all be swallowed inside. Even the asteroid belt would be consumed. Only the outer planets, Saturn and beyond, might circle safely outside its edge. To picture this, imagine our entire solar system turned into a glowing ember, planets drifting like dust motes inside a colossal furnace. Volume is perhaps the easiest way to make the scale concrete. The Sun, immense as it feels to us, could fit inside uyscuti not once, not 1,000 times, but more than 5 billion times by volume. That number is almost meaningless to human intuition. 5 billion of anything is hard to grasp. But perhaps think of it this way. If each sun were a marble, filling them inside uyscuti would take enough marbles to cover entire continents in a glittering layer. The comparison is almost playful, but it is the only way to even begin wrapping the mind around the difference. And yet, for all its volume, uyscuti is not the most massive star. Its mass is estimated to be only about 30 times that of the Sun. That is heavy by ordinary standards, but far less than the compact blue giants that can reach 100 or even 200 solar masses. Uyscuti is not heavy so much as it is puffed up. Its outer layers are extended, stretched thin, making the star a kind of stellar balloon. This is part of what makes it unstable. Its atmosphere is fragile, easily disturbed, constantly shifting. Astronomers classify it as a pulsating variable, meaning its brightness changes as it expands and contracts, a slow breathing in and out that can last hundreds of days per cycle. This variability is not just cosmetic, it tells us about the interior of the star. When uyscuti pulses, its outer layers rise and fall in response to changes in pressure and fusion deep within. The light we see from Earth waxes and wanes as the star adjusts itself. Studying these rhythms helps astronomers understand how energy moves through a star so bloated, how radiation pushes outward against gravity, and how close the balance is to tipping. For a star of this size, tipping means collapse, and collapse means a violent end. The life expectancy of a star like uyscuti is short by cosmic standards. While our Sun is expected to live around 10 billion years, uyscuti will burn through its fuel in only a few million. It has already lived most of that span. Its current state as a red hypergiant marks a late phase, when hydrogen is largely exhausted in the core and heavier elements are being fused in layers. This is a star in its twilight, swollen and unstable, casting off mass into space. It will not last long. Eventually its core will no longer be able to support the crushing weight of gravity. When that moment comes, uyscuti will collapse, likely ending in a supernova, perhaps leaving behind a neutron star or even a black hole. The energy of such an explosion is difficult to overstate. A supernova from uyscuti would release as much energy in a matter of seconds as our Sun will in its entire lifetime. From thousands of light years away, it would be visible on Earth as a bright point in the sky, rivaling the brightness of the full moon, casting shadows even at night. Ancient records describe such supernovae witnessed in history, stars that suddenly appeared, blazed for weeks, then faded. If uyscuti were to explode in the next 10,000 years, future humans, or whatever life might be here, would see the night sky transformed. For now, though, it remains distant and faint. You cannot see it without a telescope, because dust and gas between us and the star dim its light. That too is telling. uyscuti is not just enormous, it is shrouded, its light softened by the interstellar medium. In some ways, it is fitting. A star so outsized it does not need to announce itself with brilliance visible to the naked eye. Its enormity is revealed only to those who look deeper, who gather its faint light and measure carefully. It is a reminder that the largest things in the universe do not always look large from where we stand. Distance and perspective can hide immensity. The numbers surrounding uyscuti often inspire comparisons. If it replaced our Sun, Earth would be lost. If it were a campfire, it would be so large you could walk for days and never reach the edge. If it were hollow, you could fit billions of Earths inside it with room to spare. These metaphors are attempts to bridge the gap between human scale and cosmic scale. None are quite sufficient, but each adds a layer of comprehension. And yet, for all its grandeur, uyscuti is fragile. The very size that makes it impressive is also its weakness. Its surface gravity is low, its atmosphere extended. Stellar winds stream outward, carrying away mass at a rate that would strip Earth bare in moments. Over time, uyscuti is losing itself to space, scattering material that will one day become part of new stars, new planets, perhaps even new life. In that sense, its excess is not wasted. It is distributed, recycled into the galaxy, part of the endless cycle of birth and death that drives the cosmos. Astronomers continue to study uyscuti not because it is unique, but because it represents an extreme. It shows what a star can become when pushed to the edge of size. It illustrates the physics of instability, the delicate balance between radiation pressure and gravity, the inevitability of collapse. It is a natural laboratory for stellar astrophysics, a case study written in light. Each observation, each refinement of its radius, mass, and variability adds to our understanding of how stars live and die. If you close your eyes and imagine standing near such a star, not that you could survive the heat, the radiation, or the winds, you might picture a horizon filled entirely with glowing red plasma, stretching beyond sight in every direction. The scale would be so vast that the curve of the star would feel like a flat plane beneath your feet. The light would saturate everything. The heat would be beyond endurance. It would be like standing on the edge of creation itself, watching matter turn into energy at a rate that defies comprehension. And yet, at its core, the same process is happening as in our Sun. hydrogen fusing into helium, atoms colliding, light being born. The difference is only scale, the same principle magnified to excess. Thinking of uyscuti in this way is humbling. Here we are, tiny beings on a small planet orbiting a modest star, and out there, a star exists that makes our sun seem like an ember. And yet, both stars obey the same laws of physics, follow the same rules, live within the same universe. The difference lies only in degree. That, perhaps, is the most striking lesson. The cosmos does not need new rules to produce giants. It only needs to apply the same rules on a larger canvas. So when we speak of the biggest star in the universe, we are not just reciting numbers. We are telling a story about scale, about how the familiar can stretch into the unimaginable. Uyscuti may not be the heaviest, it may not be the brightest, but in terms of size, radius and volume, it is a champion. It defies scale not because we cannot measure it, but because even when we do, the numbers strain against human imagination. And as we let the thought of uyscuti settle, glowing quietly in scutum, breathing slowly in and out, we can begin to wonder about the tools we use to measure such things. How do astronomers, looking across thousands of light years through clouds of dust and interference, manage to calculate the size of a star that dwarfs everything we know? When you first hear that a star is 1,000 times wider than the sun, or weighs hundreds of times more, it might sound like someone simply put it on a cosmic scale and read the result. But of course, no one is out there holding a ruler up to uyscuti or putting R136A1 on a giant balance. Every number we know about the bigger stars comes from careful, patient inference. Astronomers do not measure directly. They observe, they compare, and they calculate. Measuring the unmeasurable is one of science's quiet triumphs, and nowhere is that clearer than in the study of stars. The first tool astronomers rely on is light. Light is the messenger, travelling across space for thousands, sometimes millions of years, carrying with it information about its source. A star does not just shine uniformly. Its light carries fingerprints, subtle patterns imprinted by the elements inside it. When that light is spread out into a spectrum, like a rainbow split through a prism, it reveals dark lines where specific wavelengths have been absorbed. These absorption lines correspond to elements: hydrogen, helium, calcium, iron. From them, astronomers learn the composition of the star's outer layers. But even more than that, the spectrum tells temperature. Hotter stars radiate more blue light, cooler ones more red. By matching the spectrum to models of stellar atmospheres, scientists can deduce how hot the surface is. Once you know temperature and brightness, another step follows. The total energy a star emits, its luminosity, depends on both. A hotter surface shines more brightly per unit area. A larger surface area shines more overall. So by comparing the observed brightness of a star to its intrinsic temperature, astronomers can estimate its size. This is how stars like uyscuti earn their colossal radii. The light we receive is faint because of distance, but once corrected for how far away it is and how cool or hot it appears, the implied surface area is immense. Distance, though, is a challenge of its own. How far away is uyscuti really? For nearby stars, astronomers use parallax, measuring how the star's apparent position shifts against background stars as Earth orbits the Sun. This is the same principle your eyes use for depth perception, noticing how an object shifts relative to the background when viewed from two angles. But for stars thousands of light years away, the parallax shift is so tiny it can barely be detected. Only with space telescopes like Gaia has precision improved enough to measure such minuscule shifts. Still, for many distant giants, distance estimates remain uncertain, and because luminosity depends on distance squared, even small errors balloon into large uncertainties about a star's true size. That uncertainty is part of why the largest star changes from time to time. Measurements are refined, distances recalibrated, and suddenly the estimated radius of a star shifts. A giant thought to be the champion might shrink in rank when new data emerges. Uyscuti's title itself has been debated. Some analyses suggest it may not be quite as large as earlier believed, though still among the leaders. This is not failure but progress. Each refinement brings us closer to reality, even if it changes the scoreboard. Mass is trickier still. You cannot weigh a star directly, but gravity leaves clues. In binary systems, where two stars orbit each other, astronomers can watch their dance. By measuring the period of orbit and the distance between them, Newton's laws reveal the mass. This is one of the most reliable ways to weigh stars. For solitary giants, the task is harder. Astronomers must rely on models of stellar structure, matching observed brightness and temperature to theoretical predictions about what mass is needed to produce them. The results are less certain, but still remarkably effective. Consider R136-1, the famously massive star in the Tarantula Nebula. It is not alone. It is part of a dense cluster of stars, all young, all luminous. By studying the interactions and spectra of these stars together, astronomers can constrain the mass of R136-A1. It emerges as a monster, estimated at over 200 solar masses. But again, uncertainties remain. Some argue the mass may be lower, perhaps nearer to 150. Others suggest the upper estimates hold. Either way, it is far heavier than uyscuti, even though it is not nearly as wide. Brightness too requires care. The light that reaches Earth is dimmed by interstellar dust, tiny grains of carbon and silicates drifting through space. This dust absorbs and scatters blue light more strongly than red, making distant stars appear redder and fainter than they truly are. Correcting for this reddening requires measuring how much the spectrum has shifted. Only then can astronomers recover the intrinsic brightness. For stars near the plane of the Milky Way, where dust is thick, these corrections are crucial. Uyscuti sits in such a dusty region, which is part of why it remains invisible to the naked eye. Without correcting for that dust, its true luminosity would be underestimated. Beyond optical light, astronomers use other wavelengths. Infrared telescopes can peer through dust that blocks visible light. Radio observations can trace the gas and winds flowing from a star. Ultraviolet data reveals the hottest, most energetic emissions. Together, these paint a fuller picture, allowing size, mass, and brightness to be pinned down with greater confidence. It is like building a portrait from fragments of colour, each wavelength filling in what others cannot show. Another approach to mass comes from the physics of how luminous a star can be. There is a theoretical limit, called the Eddington limit, which sets the maximum brightness a star of a given mass can sustain before radiation pressure pushes matter away faster than gravity can hold it. By observing how close a star seems to this limit, astronomers can estimate its mass. If a star shines with 10 times the luminosity expected for its mass, something must be wrong. Either the mass is underestimated or the luminosity overestimated. Reconciling these numbers is part of the puzzle. It is worth pausing to appreciate how extraordinary this is. From thousands of light years away, astronomers can determine the size of a star, the weight of its core, the speed of its winds, the cycle of its pulsations. They cannot touch it, cannot orbit it, cannot drop instruments into it. All they have is light. Yet light, with enough patience and physics, reveals nearly everything. Of course, uncertainty never vanishes. Astronomers often present ranges, a radius between a 500 and a 700 times the Sun, a mass between 25 and 40 solar masses. But even those ranges represent an astonishing narrowing of possibilities. To pin down the traits of something so distant, so unstable, so immense, is an achievement built on centuries of effort, from the first catalogues of stars to modern space telescopes. The act of measuring also shapes how we imagine. Before distance measurements were precise, stars were assumed to be like the Sun, only farther. It took parallax to prove that stars differ dramatically in intrinsic brightness. Before spectroscopy, stars were just coloured dots. It took the splitting of light to reveal their temperatures and compositions. Before binary orbits were tracked, mass was an unknown. Each new tool deepened the picture, each step refining our sense of what biggest truly means. And as with all science, humility remains. Uyscuti may or may not be the largest star by radius. R136A1 may or may not hold the crown for mass. New data might dethrone them, might reveal even larger giants hidden by dust or distance. What we call the biggest today is only the biggest we have measured so far. The universe may have surprises still waiting, stars so immense they make uyscuti look modest. If they exist, they are hidden behind the veil of distance and obscuration, awaiting instruments sensitive enough to find them. In that way, measuring the unmeasurable is not just about numbers. It is about the frontier between what we know and what we might still discover. Every estimate carries a reminder. This is as far as we can see now, but beyond lies more. And that perhaps is the most comforting truth. The universe is never finished giving us puzzles. So when we read that uyscuti is 1/700 times the radius of the Sun, or that R136A1 weighs 200 solar masses, we are not reading absolute certainties. We are reading the best understanding of the moment, the product of light gathered across time and space, sifted through equations, corrected for dust, refined by models. They are approximations, but approximations so remarkable that they let us hold immensity in mind. And with those numbers in place, with size and mass and brightness sketched into view, we can turn to the next question. What does that power actually mean? How much light does a giant star shed? How does its glow compare to our Sun, to the entire galaxy, to the boundaries of our imagination? Light has always been one of the most fundamental ways we know a star. Before anyone measured parallax, before telescopes split spectra into rainbows, before we had the language of fusion or luminosity, people simply looked up and noticed brightness. Some stars twinkled faintly, others burned so brightly they became landmarks in the sky, guiding travellers and shaping myths. Even without knowing why, brightness was the clue that some stars were not like the others, and yet what the eye sees is only the beginning. A star can look bright because it is close, like Sirius, the dog star, which outshines all others in the night sky not because it is the most powerful, but because it happens to be one of the nearest. Another star can look faint because it is far away, even if it is millions of times more luminous than Sirius. Distance disguises power. Dust dims it further. The glow we see is often a softened echo of the true brilliance. When astronomers talk about luminosity, they mean the total energy a star emits every second in all directions. It is not just how bright it looks to us, but how much light it actually produces, measured across the entire electromagnetic spectrum, from invisible radio waves to blinding gamma rays. It is the real output, the raw furnace of a star's core translated into radiation. And when we compare stars in this way, the difference between our Sun and the giants becomes staggering. Our Sun, by definition, has a luminosity of 1 solar unit. That is about 3.8 10^26 watts. To put that in perspective, it is the equivalent of 10 billion nuclear bombs exploding every second. That is the steady power we live under, the gentle warmth that drives weather and fuels photosynthesis. It feels immense, and it is. Yet compared to the giants, it is modest. A typical red supergiant like Betelgeuse emits around 100,000 times the Sun's luminosity. A blue supergiant like Rigel radiates more than 100,000 times as well, concentrated in hotter, bluer light. The most luminous known stars like Eta Carinae or R136A1 shine with several million times the Sun's brightness. Imagine multiplying those 10 billion nuclear bombs per second by millions. That is the scale of light we are speaking of. One way to appreciate this is to imagine sitting at different distances from such a star. If Earth orbited a supergiant instead of the Sun, it would not survive. The oceans would boil away instantly. The crust would melt, the atmosphere would be stripped. Even at distances where Pluto orbits, the heat and radiation would be lethal. To find a habitable zone around a hypergiant, you would need to orbit so far away that the star itself would appear as large as the Sun does in our sky, even from billions of kilometres. The balance between distance and brightness shifts dramatically. But even this thought experiment has limits, because hypergiants are not stable enough to host planetary systems for long. Their luminosity is tied to their short lifespans. They burn through their fuel so quickly that no planet could count on a steady climate for billions of years. The very brilliance that makes them spectacular also makes them inhospitable. The glow of giants is not just powerful, it is influential. A single hypergiant can dominate its region of space. Its radiation ionizes nearby gas, stripping electrons from atoms, creating glowing nebulae that stretch for light years. Its stellar winds push material outward, sculpting clouds into arcs and cavities. Its brightness provides navigation beacons even for astronomers across galaxies. In some cases, these stars are so luminous that they can be seen in neighbouring galaxies with modest telescopes, their glow outshining clusters of smaller stars combined. Consider Eta Carinae, one of the most luminous stars in our galaxy. In the 19th century, it underwent a massive eruption, brightening so much that it became the second brightest star in the sky for a time. For years, people could see it without difficulty, even though it is over 7,000 light-years away. The amount of energy released in that eruption alone was equivalent to our Sun's entire lifetime output. And yet Eta Carinae survived, dimmed again, and continues to glow today. That glow is not steady. It is restless, unpredictable, flickering with the turbulence of an unstable giant. The colour of a giant's glow tells another story. Red supergiants, cool at their swollen surfaces, emit most of their light in the red and infrared part of the spectrum. They look ruddy to the eye, sometimes orange, sometimes almost blood red. Blue giants, burning hotter, emit light more in the blue and ultraviolet. To the eye they look icy white or electric blue. But beyond what we can see, their ultraviolet output is tremendous, bathing nearby space in invisible radiation that shapes the chemistry of entire regions. This distinction between red and blue is more than cosmetic. It reflects the life stage of the star. Giants that have swelled into red are nearing their ends, their outer layers expanded, their cores fusing heavier elements. Blue giants are younger, still burning hydrogen or just beginning to fuse helium, their cores hotter and more compressed. The glow tells you not just how bright the star is, but where it is in its journey. Astronomers measure luminosity in solar units because the raw numbers are too large for daily use. Saying a star radiates 10 million times the energy of the Sun is easier to grasp than reciting 3.1033 watts. Even so, the comparison remains almost abstract. Human intuition cannot truly hold the power of millions of suns. We can calculate it, we can write it down, we can simulate its effects, but we cannot feel it directly. What we feel is our own sun, warm on the skin, bright in the sky. That is the limit of direct experience. Beyond that, imagination must take over, and imagination does help. Think of the glow of a giant star like a bonfire compared to a candle. The candle illuminates a corner of a room. The bonfire illuminates an entire forest clearing, casting shadows far into the trees. Now scale that up by factors of millions, and the bonfire becomes a hypergiant star, casting its glow across interstellar space, shaping the very structure of its surroundings. The metaphor is still inadequate, but it gives a sense of proportion. The glow is also fleeting. Hypergiants spend only a few million years in these brilliant phases before collapsing. In cosmic terms, they are shooting stars on a grand scale, brief flashes compared to the billions of years of smaller stars. Their luminosity is unsustainable, a flare before the fall. That is why they are rare. For every hypergiant in the galaxy, there are billions of dim red dwarfs, glowing faintly but enduringly. Most of the light in the universe is spread among the humble, not the extravagant. But the extravagant are the ones we notice, the ones that burn their names into history. The sheer intensity of a giant's glow also has consequences for what comes next. The light pressure, the outward push of photons, can strip away material from the star. Radiation pressure is not just metaphorical, it is physical. Photons carry momentum, and when enough of them stream outward, they exert force. This force pushes on the star's outer layers, driving stellar winds, carving away at the very mass that sustains fusion. The brighter the star, the stronger this push, the faster it loses material. In a sense, its own light is working against it, hastening its end. From Earth, the glow of giants is filtered through atmosphere and distance. We see Betelgeuse as a reddish star, Rigel as a bluish one, Antares glowing low in the southern sky. They are points of colour against darkness, remarkable but still small to the naked eye. Knowing what they truly are, though, changes the experience. That faint red dot is radiating more energy than our sun by factors of tens of thousands. That faint blue point is blazing so hot that it shapes nebulae light years wide. What looks like a star among stars is in truth a titan among embers. The glow of giants is not just a spectacle, it is also a gift. The radiation they release includes photons energetic enough to trigger chemical reactions in nearby gas clouds. These reactions can spark the collapse of material into new stars. In this way, the brilliance of one generation seeds the next. The glow becomes the midwife of new suns, ensuring the cycle of stellar birth continues. Without the luminous push of giants, the galaxy would be slower, quieter, less fertile. There is also the question of what happens when the glow stops. When a giant collapses, its luminosity plummets. In its place might be a neutron star, radiating in pulses, or a black hole, dark and silent. The transition from radiance to darkness is abrupt. A star that outshines millions can disappear in an instant, leaving only an echo in the form of an expanding shell of gas. But even in that silence, the light it released across its lifetime continues to travel. Photons that left Betelgeuse centuries ago are still streaming through space, some just now reaching our eyes. The glow of giants, once unleashed, does not vanish immediately. It lingers, it travels, it carries the story forward. So when we ask how powerful the biggest star is, luminosity is one of the clearest answers. Power is light, light is energy, and giants release energy at rates beyond comprehension. Their glow is not just beyond imagination in scale, but beyond it in consequence. It shapes space, it shapes time, it shapes the very possibility of life. The glow is not just a number, it is a force, one that reaches across gulfs of emptiness to touch us, however faintly, here on a small planet orbiting a modest star. What if somehow our sun were replaced by such a giant? What would it be like to live beneath the light of a hypergiant? To feel its glow not from afar but from within our own sky? Imagine, just for a moment, that the sun we know so well is suddenly gone, and in its place stands one of the giants. Perhaps uyscuti, perhaps Betelgeuse, perhaps a massive blue supergiant blazing with ultraviolet light. It is, of course, only a thought experiment. Nothing of the kind is actually happening, and if it did, we would not be here to tell the story. But imagining it allows us to grasp more vividly the true scale of these stars. When we measure them from afar, the numbers remain abstract. When we place them into the familiar landscape of our solar system, the reality becomes sharper. From the surface of Earth, the sky would be unrecognizable. Instead of the steady yellow-white sun that arcs gently from horizon to horizon, the entire dome of the heavens would blaze with light. A star like uyscuti, if placed at the centre, would stretch outward until its outer atmosphere extended far beyond Earth's orbit. We would not exist as an orbiting planet at all. Earth would be swallowed whole, its rocks and oceans vaporized within the churning plasma of the star's bloated envelope. But let us shift the scenario slightly. Instead of imagining Earth inside the star itself, picture that Earth, somehow, exists at a distance where it could orbit safely, just beyond the giant surface. To achieve anything resembling habitability, our planet would need to be billions of kilometers away. The habitable zone, that delicate band where liquid water could exist, would move outward dramatically. Around a star millions of times brighter than the Sun, the habitable zone would not be a few dozen million kilometers out. It would be tens of billions. Earth's orbit would have to be pushed far beyond Pluto, beyond even the scattered icy bodies of the Kuiper Belt, in order to receive the same gentle warmth we now enjoy. If Earth were somehow relocated there, the Sun would no longer appear as a small disk in the sky. The hypergiant would dominate the horizon, its glowing surface spanning a vast portion of the heavens. Even from billions of kilometers away, its apparent size would dwarf the Sun we know. Instead of a blinding pinpoint, the sky would be filled with a glowing, turbulent expanse of red or blue light. Clouds of plasma, convective cells larger than Earth itself, would drift visibly across the surface, like storm systems the size of planets. Watching the sky would no longer mean tracking a tiny golden circle. It would mean living under a ceiling of fire. The light itself would feel different. Around a red hypergiant, the glow would be deep, ruddy, saturated in orange and infrared. Shadows would stretch long and soft, painted in crimson tones. Around a blue supergiant, the light would be harsh and icy, rich in ultraviolet that our eyes cannot see, but our skin would feel instantly. Plants, if any could exist, would need to evolve under entirely different conditions, absorbing different wavelengths, adapting to the intensity. Our biology, tuned to the stable sunlight of a yellow dwarf, would not recognize this radiance as home. Radiation would be the first and greatest danger. Hypergiants emit torrents of ultraviolet and even X-rays. The Earth's magnetic field and atmosphere, so effective at shielding us from the sun's modest wind, would be overwhelmed. The air would ionize. The oceans would glow with ultraviolet fluorescence before boiling away. No biosphere as we know it could survive. The very fabric of the planet would be scorched. Even if we look past habitability, the gravitational influence would remake our solar system. The mass of a hypergiant might be dozens of times that of the Sun. Or it might be less than we imagine, since red hypergiants, despite their volume, are not especially dense. But in either case, orbital distances and planetary paths would shift. Gas giants might be destabilized. Asteroids could be ejected. The fragile architecture of our solar neighborhood would dissolve under the tug of a star so alien. Time itself would feel different, in a metaphorical sense. Our sun rises and sets with a rhythm that defines life. A hypergiant, unstable and variable, would not provide the same constancy. Its brightness would swell and fade over months or years. Seasons would no longer be tied to the tilt of Earth's axis, but to the breathing of the star itself. One year it might blaze hotter, the next cooler, each change altering the balance of radiation across its domain. For any imagined observers, time would be measured not in hours and days, but in the restless cycles of the giant overhead. And then there is the question of lifespan. Living under a hypergiant would mean living with an inevitable doom. These stars do not last. They shine brightly for a few million years at most. If our sun were replaced by such a star, we would inherit a future counted not in billions of years, but in millions. From the very start, the countdown to supernova would already be ticking. The sky might be brilliant, but it would also be haunted by the knowledge that the brilliance could end in an explosion powerful enough to sterilize everything in sight. To make the vision more tangible, imagine the final moment. One day, after millions of years of unstable burning, the core collapses. The star shudders, rebounds, and detonates in a supernova. the light increases 1,000,000,000-fold. For days, even weeks, the sky is brighter than the full moon, perhaps even visible in daylight. From Earth, there is no escaping the flash. Radiation sweeps outward. Shock waves rush through space. The habitable zone, if any existed, is obliterated. The beauty of the sky ends in violence. And yet, in another sense, such a replacement would be fruitful. The explosion would scatter elements, iron, carbon, oxygen, silicon, into space, enriching the interstellar medium. The debris would drift for millions of years, eventually coalescing into new stars, new planets, and perhaps, one day, new life. The destruction of one planetary system would plant the seeds of countless others. It is a cycle written into the nature of giants. Live fast, burn bright, die violently, and give generously to what comes next. This thought experiment, unsettling as it is, reveals the measure of a star's power more vividly than numbers alone. It shows us that replacing our modest sun with a hypergiant would erase everything we know, reshape the very architecture of the solar system, alter the light in the sky, and shorten the timescale of existence. It makes clear that we survive only because we orbit a star that is small enough, steady enough, and long-lived enough to nurture life patiently. Giants may impress us with their size and luminosity, but they are not caretakers. They are destroyers, brilliant but fleeting. Even so, imagining such a world reminds us of the extraordinary diversity of stars. Our sun is ordinary, but that ordinariness is precisely what allows us to exist. A hypergiant would be spectacular, but spectacular in ways that leave no room for fragile biology. It is a humbling balance that the biggest stars in the universe, the ones that defy scale and blaze with unimaginable light, cannot host life the way our small, steady sun does. Their power is too much, their fire too fierce, and so we find ourselves grateful, perhaps, to orbit something modest, to receive just enough warmth, just enough light, and just enough time to allow oceans and forests and civilizations to rise. From afar, the glow of giants inspires awe. Up close, it would annihilate. Power is relative, and in the universe, power often comes at the expense of stability. When you look up at the night sky, every star you see seems to be part of a flat dome above you. They all appear at more or less the same distance, as if someone sprinkled bright dust across a black ceiling. The brightest stand out, the faintest fade to the edges, but the depth is hidden. Your eyes and brain are not built to perceive how far each one really is. The sky feels immediate, intimate, close enough that you could almost reach out and touch the dots. Yet those dots are scattered across unimaginable gulfs of space. Some of the brighter ones are only a few light years away, others hundreds, and still others thousands. The distances are so enormous that no human sense can truly comprehend them. This is why a star like uyscuti, one of the largest ever measured, is invisible without a telescope. It sits about 9,500 light-years away, far beyond the range of human sight, tucked into a region of the Milky Way rich with dust and gas. Its light, already dim by distance, is further muted by the material between. By the time it arrives at Earth, it is faint, almost lost among the crowd. In contrast, Sirius, just 8.6 light-years away, shines brilliantly as the brightest star in our sky. It is bright not because it is the most powerful, but because it is close. The paradox is that the truly enormous stars often feel far less impressive to our eyes than the modest ones that happen to be nearby. To put distance into perspective, consider light itself. Light travels at about 300,000 kilometers per second. In a single second, it could circle Earth more than 7 times. Yet even at that speed, it takes over 8 minutes for sunlight to reach us. That means when you look at the sun, you are seeing it not as it is now, but as it was 8 minutes ago. For the nearest star beyond the sun, Proxima Centauri, the light takes over 4 years to arrive. For uyscuti, it is nearly 10,000 years. The photons entering your eyes tonight left that star when human civilization was still in its earlier stages, long before the rise of cities, long before writing. Every glance into the night is a glance into history. This delay creates a strange intimacy. You see the star as it was, not as it is, and yet the connection feels immediate. The light touches you directly, carrying the memory of a place across thousands of years of emptiness. In that sense, even distant stars feel close. They appear as small, steady points, and their light is personal, entering your eye, activating cells in your retina. You feel their presence as if they are neighbours. But in reality, the distances are so vast that if you travelled at the speed of a commercial airplane, it would take millions of years to reach even the closest one. Astronomers deal with this challenge by inventing units to make distances more manageable. A light year is one. A parsec, equal to about 3.26 light years, is another. These units are shorthand, ways of handling the immensity, but for the rest of us, the scale remains slippery. You can say uyscuti is 9,500 light years away, but what does that mean to the human mind? You can compare it to the sun's distance, but the ratio, 63 trillion times farther, is so large that it becomes abstract. The numbers inform, but they do not settle into intuition. And yet distance is not just an obstacle. It is part of what allows us to see the universe at all. If stars were closer, their light would overwhelm us. The night sky would be filled with blinding fire. If they were farther, their light would fade beyond detection. We exist in a narrow zone where stars are distant enough to be safe, but near enough to be visible. That balance gives us constellations, navigation, wonder. It also gives astronomers the chance to study giants from a safe remove. Uyscuti may be unimaginably bright, but from 9,500 light years away it is harmless. Its eventual supernova will be spectacular, but it will not threaten Earth. Distance protects as much as it hides. Dust complicates the picture further. Between us and the giant stars lies the interstellar medium, not empty but filled with particles. Carbon, silicates, icy grains, spread thinly across vast volumes. Over thousands of light years, even sparse material can accumulate into a thick veil. Dust absorbs and scatters starlight, especially the shorter blue wavelengths, making distant stars appear redder and dimmer. This is why uyscuti, despite being so large and luminous, remains invisible to the unaided eye. Its light has been softened by its long journey. In a sense, we do not see the star itself, but a filtered version, altered by the medium between. This filtering creates another paradox. The brightest stars in the galaxy may not be the ones we notice. They may be hidden behind clouds of dust, their light visible only to infrared telescopes that can pierce the obscuration. When astronomers scan the sky in infrared, entire populations of giants emerge, invisible in ordinary light. The universe we see with our eyes is only a fraction of what exists. Distance and dust together create illusions, making some stars appear close, others distant, some bright, others faint. Only careful measurement can sort the reality from the appearance. But even when the numbers are known, the feeling remains the same. Stars look close because their light is immediate. They feel personal because their photons enter your eyes, and yet they are unimaginably far. Holding both truths at once is part of the wonder of astronomy. The night sky is intimate and remote, familiar and alien, present and ancient. It also raises the question of perspective. Our sun is close, and therefore large in our sky. It dominates the day, fills the sky with light, warms the ground beneath our feet. But from a distance of a few light years, the sun would be just another faint star. If you lived on a planet orbiting Proxima Centauri and looked back, the sun would be invisible to your naked eye. It would not stand out at all. The star that sustains us completely would look ordinary, unremarkable, just one point among billions. This is the mirror of what happens with giants. To us they are faint specks. To any planets orbiting them, they would be overwhelming, dominating their skies. what is bright and what is faint depends on where you stand. Thinking about this helps us understand the scale of the universe not just with numbers, but with perspective. The reason big stars feel close yet distant is not a contradiction. It is the nature of light. It is both immediate and ancient, both personal and remote. It touches us directly, even as it comes from across the galaxy. It makes giants into neighbours, even as they sit beyond reach. Astronomers sometimes call this the problem of dynamic range. Human senses evolved for Earth, for distances measured in metres or kilometres. We can judge how far away a tree is, how large a mountain appears, how bright a fire burns. But stars exist on scales billions of times beyond that. Our brains cannot scale up easily. Instead, we rely on imagination, on metaphor, on comparisons that bridge the gap. Numbers give precision, but imagination gives meaning. Without imagination, distance would remain only abstract. So perhaps when you next look at the night sky, you might let yourself feel both truths at once. That the stars are close because their light is here now, in your eyes, and that they are distant because they sit across gulfs so vast that the mind falters. That duality is not a contradiction to be solved, but a mystery to be accepted. It is what makes the night sky what it is, a place where distance and closeness collapse into a single experience of wonder. And as we settle into that thought, as we rest with the strange intimacy of light crossing distance, we can begin to wonder about the daily lives of the stars themselves. If they seem close yet far to us, what is it like within their own existence? What would it mean to imagine the rhythm of their days, the processes inside them, the cycles of energy that unfold every moment? If you picture the life of a star, it might seem strange to think of it having days. A star does not rise and set where it lives. It does not experience the passage of time in the way we do, divided by the spin of a planet beneath it. And yet, if you imagine standing at some safe distance from a supergiant, watching it steadily, you might begin to see that it does, in its own way, have rhythms. Not days as we count them, but cycles, pulses, and processes that unfold constantly, creating a kind of stellar routine. On its surface, a supergiant is anything but calm. What looks like a glowing disk from afar is, up close, a boiling expanse of plasma. Immense convection cells churn slowly, each one so large it could engulf Earth. These cells rise from the star's interior, carrying heat upward, then sink back down after releasing their energy. Where our sun has millions of small granules bubbling across its surface, a supergiant might have only a handful, each spanning a significant fraction of its surface. To watch them drift and swirl would be like watching continents move across a globe, except they are not solid land but luminous seas of gas, glowing and shifting over months and years. Above that surface, the atmosphere of a supergiant is not sharply defined. Unlike Earth's crisp horizon, a star's edge is fuzzy, blurred. The gas thins gradually with distance, stretching outward for millions of kilometres. Within this extended atmosphere, shock waves ripple, winds stream outward, and matter constantly escapes into space. The star is shedding itself particle by particle, ton by ton, in a ceaseless flow. On Earth, we might describe a windy day, a storm, a breeze. For a supergiant, every day is windy, every day stormy, with gales carrying away mass equal to entire planets over time. Inside the star, the routine is even more intense. The core burns furiously, fusing elements in concentric layers like the rings of an onion. At the centre, hydrogen may already be exhausted, replaced by helium fusion. Around it, shells of hydrogen, helium, carbon and oxygen burn in sequence, each feeding energy outward. The balance between gravity pulling in and radiation pushing out is delicate. In a supergiant, that balance is precarious. shifting as fuel is consumed. The result is instability, felt on the surface as pulsations, cycles of expansion and contraction. From afar we see the star brighten and dim, but up close you would feel the surface swell outward, then fall back, in slow breaths lasting months or years. This breathing defines much of a supergiant's day. Not minutes or hours, but long, slow cycles, each one a heartbeat in its short, brilliant life. Imagine living on a world orbiting such a star, if such a world could exist. The sky would brighten and fade across long stretches of time, a rhythm too slow for a single lifetime but clear across generations. The seasons of light would not be tied to tilt or orbit, but to the star's own breathing. Radiation pours outward in every moment. Unlike the sun, whose brightness is steady and familiar, a supergiant's radiance is overwhelming, its energy spilling across the spectrum. The ultraviolet light scorches nearby gas clouds, making them glow in response. Infrared light seeps into space, carrying away heat. X-rays burst from turbulent winds colliding. In a single second, the star releases more energy than humanity has used in all of history. That constant outpouring is the background of its day, the steady heartbeat of brilliance. And yet, for all its violence, a supergiant is not chaotic in the way of an explosion. It holds together, maintains structure, endures across millions of years. Its day-to-day existence is steady enough to appear unchanging to us, even though beneath the surface, forces of incredible magnitude are at work. The scale is so vast that what we call daily processes may last longer than human civilizations. A day in the life of a supergiant is not a literal day, but a metaphor for these ongoing processes that shape its existence. There are also the winds, ceaseless and strong. Unlike the sun's solar wind, which streams outward but remains relatively gentle, a supergiant stellar wind can carry away billions of tons of material each second. This material does not vanish. It collects into shells and arcs around the star, visible through telescopes as glowing halos. Over time, these shells mark the history of the star's instability, records of its outflow. If you could stand far enough away to see the system as a whole, you would watch arcs of gas expand outward, like ripples on water, recording each cycle of shedding. These ripples are part of its daily existence, signs of its restlessness. And then there is rotation. Stars spin, though supergiants often rotate more slowly than their younger, smaller counterparts. Still, the motion is there. From afar it is imperceptible, but up close, the slow turning would carry convection cells across the surface, change the angle of pulsations, mix the outflowing winds. The rotation links the inner and outer processes, ensuring that material is spread unevenly, sculpting asymmetries in the shells around it. A supergiant's day includes this rotation, a slow turning of an immense body that dwarfs all planets. Time for such a star is measured differently. Our days are 24 hours marked by a planet's spin. A supergiant's time is marked by nuclear processes, by cycles of fusion, by the gradual consumption of elements. The shift from one fuel to another, the exhaustion of hydrogen, the onset of helium burning, the transition to carbon, these are the milestones. Each marks a new stage, a new pattern of behaviour. To call them days is imprecise, but they are the closest thing to rhythms we can imagine for such beings. From our vantage point, a supergiant seems eternal. Betelgeuse has shone in Orion for as long as humanity has recorded constellations. Uyscuti has pulsed for thousands of years without notice. Their days are so long that to us they feel timeless, and yet, in the life of the universe, they are brief. Their days are numbered not in billions, but in millions. Compared to red dwarfs, which may live for trillions of years, supergiants are fleeting. Their daily brilliance is unsustainable, their routine a sprint rather than a marathon. It is this contrast that makes their lives fascinating. To imagine a day in the life of a supergiant is to imagine processes so immense they blur into stability, yet so unstable they cannot last. It is to imagine a being both steady and doomed, radiant and fragile. Its day is filled with light, winds, pulsations, and the steady churn of fusion. Its night never comes, but its end is always approaching. And if you look deeper, you might even see the way these daily processes prepare the star for its final act. Each pulsation sheds more material. Each wind carries away more mass. Each cycle of fusion builds heavier elements in the core. Day by day, the star moves closer to collapse. The life of a supergiant is not just a series of stable days, but a countdown, each one a step toward the inevitable. And yet, while it lasts, the brilliance is unmatched. For us, imagining these days is both humbling and comforting. Humbling, because the scale is so far beyond our own. Comforting, because it shows that even the most powerful entities in the cosmos have routines, rhythms, and patterns. They are not chaos, but order. Not random, but structured. They live their days just as we do, within the boundaries of their nature, following cycles that sustain them until they cannot. Deep inside every star lies its true engine. What we see on the outside, the glow, the winds, the pulsations, is only the surface expression of something far more powerful happening within. For a supergiant, that engine is both its gift and its curse. It is the fusion of atoms, the tempest at the heart of giants, that makes them shine with such brilliance. But it is also what drives them to live fast and die young. Fusion begins with hydrogen. In the cores of stars like our Sun, hydrogen atoms are squeezed together until they merge, releasing energy in the process. Each fusion reaction converts a small fraction of mass into light, a transformation first hinted at by Einstein's famous equation E mc2. A tiny amount of matter becomes an enormous amount of energy. This is why the Sun can shine steadily for billions of years, consuming 4 million tons of hydrogen every second, and still seem unchanged. Its supply is vast, its burning controlled, its balance stable. But in a supergiant, everything is turned up to extremes. The greater the mass of the star, the stronger its gravity, and the more intense the pressure at its core. Temperatures soar to hundreds of millions of degrees. Fusion does not just proceed, it races. Hydrogen is burned at a furious pace, billions of times faster than in smaller stars. The energy output is so overwhelming that radiation pushes violently outward, swelling the star to incredible size. This outward push balances gravity, keeping the star from collapsing, but it also makes the star unstable. The balance is delicate, precarious, always on the edge of tipping. As hydrogen runs low in the core, the fusion furnace shifts. The star begins fusing helium into carbon and oxygen. Around the new helium-burning core, a shell of hydrogen continues to fuse. Further out, layers form where heavier elements ignite. In the most massive supergiants, this sequence continues until iron is reached. Each step is faster than the last. Hydrogen fusion may last millions of years. Helium fusion may last a few 100,000. Carbon, neon, oxygen, and silicon burn for shorter and shorter spans, sometimes mere years or even days. The star's core becomes an onion-like structure, shells of different elements burning simultaneously, each feeding energy outward. This layered burning is the hallmark of a giant in its final stages. It is the tempest within, raging with unimaginable ferocity. Entire Earth masses of carbon may be consumed in days. Fusion reactions release energy equivalent to millions of suns. Neutrinos, ghostly particles born in these reactions, stream outward, passing through the star and into space, carrying energy that we can detect here on Earth. In the laboratories of astrophysics, scientists model these processes to understand not just how stars shine, but how the universe itself evolves. One of the striking things about fusion in giants is how little of the star is truly involved. The core, where fusion happens, may be only a fraction of the total size. The outer layers, vast and bloated, are inert, carried along by the energy generated below. And yet, those layers respond to every change in the core. When fusion shifts from one element to the next, the balance alters. The star expands or contracts, brightens or dims. The tempest within is the driver of everything seen without. The violence of fusion in a giant also explains why they die so quickly. The more massive the star, the faster it burns its fuel. A star 20 times the mass of the Sun may live only 10 million years. 100 solar masses may last only a few million. By comparison, our Sun's modest mass allows it to burn slowly, stretching its life over billions of years. In this sense, giants are like candles with too much wick exposed. They blaze brilliantly, but they cannot last. Their very brightness is their downfall. Fusion in supergiants also creates the elements of the universe. Hydrogen becomes helium. Helium becomes carbon, oxygen, and neon. These, in turn, fuse into heavier elements like silicon and sulfur. At the end of the chain lies iron, but iron is different. Fusing iron does not release energy, it consumes it. When the core becomes iron, fusion can no longer support the star against gravity. The tempest within collapses. The core implodes, then rebounds, and the star explodes in a supernova. This is the inevitable fate of the most massive giants. The supernova itself is the final expression of the tempest, a release of energy so violent it outshines entire galaxies for weeks. In that instant, elements heavier than iron, gold, uranium, platinum, are forged in the blast. They are scattered across space, carried in shock waves that enrich the interstellar medium. Every atom of iron in your blood, every bit of calcium in your bones, every trace of oxygen in your lungs was once part of a star's fusion cycle, born in the tempest at the heart of giants. When you breathe, you are breathing the product of stellar furnaces. When your heart beats, it does so with iron from a long-dead star. This connection is not poetic invention, it is physical truth. Fusion in supergiants is the source of the universe's complexity. Without it, the cosmos would contain only hydrogen and helium, the primordial elements. There would be no planets, no oceans, no living beings. Fusion is creation as much as it is destruction. The tempest within is the forge of everything we know. Astronomers cannot see fusion directly. They infer it from the light emitted, from the spectra, from the pulsations and winds. They build models that simulate the pressures and temperatures of stellar cores, comparing them to observations. They detect neutrinos streaming from supernovae, confirming the processes at work. Even without touching the core, science reaches into it, revealing its secrets. For those who study stars, the tempest within is both awe-inspiring and humbling. It shows the power of simple physics, gravity, pressure, nuclear forces, scaled up to cosmic dimensions. It also reminds us that stars are not eternal. Their brilliance comes at a cost, and that cost is time. To watch a giant is to watch a life lived at full intensity, racing through stages that smaller stars take billions of years to reach. Imagining the core of a supergiant is like imagining standing at the edge of a volcano, except this volcano burns not with fire but with nuclear reactions. The heat is so extreme that matter behaves differently, stripped of electrons, crushed into plasma. Atoms collide at speeds beyond comprehension, merging into new forms, releasing bursts of energy with every fusion. The pressure is so immense that even quantum mechanics, the laws governing particles at the smallest scales, plays a role in holding matter up. The tempest within is not just heat and light, it is physics pushed to its limits. From the outside, a supergiant may seem steady. Betelgeuse shines in Orion. uyscuti glows faintly through dust, Rigel sparkles blue-white. To the naked eye, they appear timeless. But within, storms rage, layers burn, and the countdown to collapse ticks forward. Their apparent calm hides the chaos inside. To imagine their day-to-day lives without knowing the tempest is to see only half the story. It is within the heart that the true drama unfolds. And as we think about that heart, about the fusion that defines giants, we begin to see why they matter so deeply. They are not just curiosities, not just large and luminous stars in distant constellations. They are the source of the elements, the engines of galactic evolution, the crucibles of matter itself. Their tempests give rise to everything else. If you step outside on a breezy day, you can feel the movement of air against your skin. It is gentle most of the time, a soft reminder that the atmosphere around you is not still, but dynamic. Stronger winds can bend trees, lift dust, and shape landscapes over years. But no matter how powerful they seem, earthly winds are nothing compared to what flows constantly from the surfaces of stars. Every star breathes. The breath is not air but streams of charged particles, atoms stripped of electrons and hurled outward into space. These are stellar winds, and in the case of the bigger stars, their winds are so intense they can carry away the equivalent of entire worlds over their lifetimes. Our own sun produces a solar wind. It streams outward in all directions, a flow of protons and electrons moving at hundreds of kilometers per second. Though faint by cosmic standards, this wind has profound effects. It shapes the tails of comets, pushes against interstellar gas, and carves out a protective bubble around our solar system known as the heliosphere. When it interacts with Earth's magnetic field, it produces auroras, shimmering curtains of light in polar skies. That is the influence of a modest star's breath. Now imagine scaling that up by factors of thousands or millions. A red supergiant like Betelgeuse, or a hypergiant like uyscuti, does not merely exhale a gentle stream. Its atmosphere is so extended, its gravity so weak at the surface, and its radiation so intense that mass is driven outward in colossal flows. Instead of losing a small trickle of particles, these stars lose significant fractions of their mass over time. In some cases, they shed as much as one solar mass every 100,000 years. For comparison, that is like the sun expelling the mass of an entire Earth every single year. The mechanism behind these winds is varied. Radiation pressure, the force of light itself, pushes outward on atoms and dust in the atmosphere. Convection, the rise and fall of hot gas within the star, drives turbulence that flings material into space. Pulsations, the slow breathing of the star as it expands and contracts, help lift outer layers beyond the point where gravity can hold them. Once free, the gas is swept away, carried into the surrounding interstellar medium. The result is not a uniform breeze, but a tempest, sculpting the space around the star with arcs, shells, and clouds of glowing material. These outflows can be seen clearly in infrared images. Around Betelgeuse, for example, astronomers have observed multiple arcs of gas and dust extending far beyond the star itself. Each arc represents a period when mass loss was particularly strong, a record of the star's past breaths. Together, they form a halo stretching for light years. Looking at them is like reading the diary of the star's instability, written in expanding rings of plasma and dust. Hypergiants like Uyscuti majoris take this to an extreme. Observations show vast clumps and knots of gas surrounding it, ejected irregularly, as if the star is coughing rather than breathing smoothly. These eruptions can release more material in a single event than the Sun loses in centuries. They remind us that stellar winds are not always steady flows, but can also be violent, episodic, unpredictable. The consequences of such winds ripple far beyond the star itself. They enrich the interstellar medium with heavy elements, carbon, oxygen, nitrogen, all forged in the star's core, are carried outward, seeded into space where they will eventually become part of new stars and planets. Without this recycling, the galaxy would remain poor in the elements necessary for life. Stellar winds are part of the great cosmic cycle. The way matter is passed from one generation of stars to the next. They also shape their surroundings physically. The gas pushed outward collides with interstellar clouds, compressing them, sometimes triggering new star formation. The winds carve cavities, hollowing out regions of space, leaving behind bubbles tens of light years wide. In some cases, when the winds from multiple massive stars overlap, they create vast superbubbles that alter the structure of entire spiral arms of galaxies. What seems like a personal breath becomes a galactic force. Closer to home, if Earth orbited a giant star, these winds would be devastating. The constant flow of particles would strip away the atmosphere, erode magnetic fields, and sterilize the surface. Planets in such environments are unlikely to survive intact, at least not for long. This is another reason why giants, despite their beauty, are inhospitable. Their winds are too fierce, their breaths too heavy. Life requires stability, shelter, and moderation, things giants cannot provide. And yet, from a safe distance, these winds are gifts. The very atoms in our bodies once drifted in such outflows. Long before Earth existed, long before the sun was born, massive stars in earlier generations shed their material into the galaxy. That material coalesced into clouds, collapsed, and formed new stars, including ours. The winds of giants are written into our chemistry. Every breath you take is in some way connected to the breaths of stars. Astronomers study these winds not only for their role in cosmic recycling, but also for the clues they provide about the final fates of stars. The amount of mass lost determines how a star will die. A star that sheds enough may collapse into a neutron star rather than a black hole. One that holds onto more may collapse directly into a black hole. The winds are not just decoration, they shape destiny. Watching them is watching the star's end being written in advance. The study of stellar winds combines many tools. Spectroscopy reveals the speed of outflows, measured by the Doppler shift of light. Infrared imaging shows the dust carried outward, glowing with the heat of the star. Radio telescopes trace the molecules formed in cooling gas. Each wavelength reveals another piece of the puzzle. Together they show stars not as static points of light, but as dynamic beings, shedding and shaping, influencing their galaxies in real time. There is a quiet poetry in calling these processes winds. It makes something so alien feel familiar. We know what it means for the air to move, to press against us, to erode mountains, to carve dunes. Stellar winds are the same principle, magnified beyond comprehension. They are movement, force, change, expressed not in kilometres per hour, but in thousands of kilometres per second. They do not bend trees. They sweep away atmospheres, carve out nebulae, and create the raw material of worlds. And yet, even with all their violence, they are not constant chaos. They have rhythms. Pulsations drive periodic increases. Magnetic fields channel flows into particular directions. Dust condenses at certain distances, shaping arcs and shells. There is structure within the storm. A supergiant's wind is not random but patterned, a reflection of the processes inside. Studying those patterns allows astronomers to peer indirectly into the star's heart, to see how fusion and instability ripple outward. It is easy, when hearing about these vast forces, to feel small. To imagine a wind that carries away planets makes human struggles with storms seem trivial, but at the same time it can also be comforting. The same processes that seem destructive are also creative. They do not end with loss, but with renewal. Without the winds of giants, there would be no enrichment, no new stars, no new worlds. The very violence that would destroy us up close is the reason we exist at all. So perhaps the next time you feel a breeze on your face, you might remember that winds exist everywhere, from the air around us to the plasma streaming from the stars. The difference is only in scale. A gentle gust here on Earth is a small echo of the stellar winds that shape galaxies. And in that thought there is a sense of connection, a thread linking the intimate with the cosmic. When you imagine a galaxy, it is easy to think of it as a collection of countless stars, each one tiny and separate, scattered like grains of sand across a cosmic shore. And in many ways, that picture is true. The Milky Way contains hundreds of billions of stars, each with its own orbit, its own history, its own light. Yet within that vast community, there are certain stars whose influence stretches far beyond their immediate surroundings. The largest, brightest giants are not just members of the crowd, they are sculptors, architects, and disruptors, shaping the environments around them in ways that ripple across light years. A supergiant or hypergiant does not live quietly. From the moment of its birth, its sheer radiation and winds begin to alter its neighbourhood. Picture a cluster of stars forming from a dense molecular cloud. Most of the newborn stars are small, dim, destined to live long, slow lives as red dwarfs. A few, like our sun, are middling, bright enough to shine steadily for billions of years. But scattered among them are giants, massive and luminous, their presence impossible to ignore. Within only a few million years they transform the cloud that gave birth to them. Their light is the first force. Ultraviolet radiation streams outward, ionizing nearby gas, stripping electrons from atoms and causing the gas to glow. These regions, known as H2 regions, become enormous bubbles of light, hundreds of light years wide, visible even from distant galaxies. The Orion Nebula is one such region, lit by the radiation of massive young stars. Without those giants, the nebula would be dark, invisible. The glow is not just beautiful, it is a sign of the profound effect a handful of stars can have on an entire cloud. The winds of giants add another layer. Material streaming outward collides with surrounding gas, sweeping it into shells and arcs. Over time, these winds carve cavities, hollowing out the star's birthplace. In some cases, the compression of gas at the edges of these cavities triggers new star formation, as the shock waves push clouds beyond the threshold of collapse. In this way, one generation of massive stars can seed the next, not just by enriching the galaxy with heavy elements when they die, but by literally squeezing new stars into existence while they live. This interplay of light and wind creates structures on scales we can see directly. Images from telescopes like Hubble show immense bubbles, pillars and arcs in star-forming regions, all sculpted by giants. The famous pillars of creation in the Eagle Nebula are shaped by radiation and winds from massive stars nearby. The delicate columns of gas would not exist in their striking form without the presence of giants sculpting them. What seems like static beauty is, in reality, the record of constant pressure and erosion. As giants age, their influence grows even more dramatic. When they swell into red supergiants, their mass loss increases, filling their surroundings with enriched gas and dust. This material mingles with the interstellar medium, changing its composition. By the time the star finally dies in a supernova, the region is already transformed. The explosion then adds the final touch, a shock wave that races outward, sweeping up material, compressing clouds and scattering elements across vast distances. Entire star clusters can be reshaped this way. In young clusters, the most massive stars often determine how long the gas and dust linger. Without them, the clouds might persist for tens of millions of years, forming stars slowly. With them, the clouds are blown away in a fraction of that time, leaving behind only the stars. In this sense, giants set the clock for their neighbourhoods, dictating how quickly star formation begins and ends. Even on galactic scales, their effect is visible. In spiral arms, where stars are born most actively, the brightest regions often correspond to the presence of massive stars. Their light makes the arms glow, tracing the spiral pattern we see in photographs. Without giants, galaxies would look dimmer, less structured, less vibrant. Their presence gives galaxies much of their visual character. The neighbourhood effect extends further still. When multiple giants die in the same region, their supernovae overlap, creating superbubbles, vast cavities filled with hot, tenuous gas. These superbubbles can span hundreds of light years, influencing the dynamics of entire spiral arms. They act like chimneys, venting gas out of the galactic plane, connecting the disk of the galaxy to the halo above and below. In this way, the lives and deaths of a few stars help regulate the flow of matter on a galactic scale. Closer to us, we see this in the local bubble, a region of the low-density gas surrounding our solar system. Astronomers believe it was carved by multiple supernovae from massive stars millions of years ago. We live in the aftermath of their influence, in a neighbourhood shaped by giants long since gone. Their presence is recorded not only in the stars we see, but in the very medium we move through. For smaller stars and planets nearby, the influence of giants can be dangerous. Their radiation can strip atmospheres from worlds, sterilising surfaces. Their winds can erode protoplanetary disks, preventing planets from forming. Their supernovae can bathe regions in deadly radiation. To live near a giant is to live under constant risk. Yet even that danger plays a role in galactic ecology. By destroying some systems, giants clear the way for others, preventing stagnation, ensuring cycles of renewal. In human terms, the neighbourhood effect of giants is like living near a volcano. The land is fertile, enriched by minerals, but eruptions are inevitable. Life can flourish, but it must adapt to sudden destruction. Similarly, galaxies with giants are dynamic, rich and creative, but also volatile. Stability belongs to regions far from giants, where small stars dominate. This contrast helps explain why life exists around a star like ours. We orbit a modest yellow dwarf in a relatively quiet neighbourhood. Our galaxy has giants, but they are not close enough to threaten us. Their influence enriches the gas from which our solar system formed, but their violence did not disrupt our planet's development. We live in the balance point, close enough to benefit, far enough to be safe. When astronomers simulate galaxies, they must include the effects of giants to capture reality. Without them, models fail. Gas does not circulate properly, star formation proceeds incorrectly, spiral arms lose definition. The neighbourhood effect is not optional, it is essential. Giants are the regulators, the feedback mechanisms, the engines of galactic life cycles. To appreciate this fully, it helps to zoom out in imagination. Picture the Milky Way from above, its spiral arms curving gracefully. Within those arms, clusters of massive stars ignite, lighting their surroundings. Around each cluster, bubbles form, winds blow, gas compresses. Over millions of years, these bubbles merge, spiral arms churn, and the entire galaxy evolves. The giants are few, but their fingerprints are everywhere. They are not just inhabitants of the galaxy, they are agents of its ongoing transformation, and yet, as powerful as they are, their influence is not endless. They live and die quickly, leaving behind remnants, neutron stars, black holes, supernova remnants that continue to mark their place. Over time, the neighbourhood effect of one generation fades, replaced by the next. The galaxy is never static. It is always being reshaped by the latest cohort of giants. This, too, is part of the power of the larger stars. They do not exist in isolation. Their size, brightness, and winds are not just personal traits. They are forces that ripple outward, affecting clouds, clusters, arms, and entire galactic structures. To speak of their neighbourhood effect is to acknowledge that in the universe, nothing is separate. Every star lives within a web of influence, and the giants tug hardest on that web. Long before telescopes, long before equations of nuclear fusion, or the word supergiant existed, people looked up at the night sky and wondered. The stars were companions in the dark, patterns traced into constellations, stories told around fires. The largest and brightest among them drew special attention. They stood out from the countless faint points, commanding reverence and fear. To ancient eyes, these stars were not remote spheres of gas. They were deities, omens, ancestors, or guides. Their brilliance demanded meaning, and across cultures those meanings took many forms. Consider Orion, the hunter, one of the most recognizable constellations in the sky. His shoulder is marked by Betelgeuse, a red supergiant nearing the end of its life. Today we know it as a massive star 1,000 times wider than the Sun, but to ancient civilizations it was the fiery shoulder of a giant figure. The Egyptians saw Orion as Osiris, the god of rebirth, with Betelgeuse shining as one of his defining stars. The Greeks wove tales of Orion as a mighty hunter, striding across the heavens. The brightness and redness of Betelgeuse gave it special weight, as if it were a flame burning within the constellation's body. Even now, when people notice its reddish glow, they remark on its difference, its character. The star has carried myth across millennia. In the constellation of Scorpius, Antares glows bright red, rivaling Mars in colour and often confused with it. Its very name, Antares, means rival of Ares, a reference to the god of war associated with the planet Mars. To the Greeks, its hue was a sign of blood, conflict and intensity. To the Maori of New Zealand, Antares marked important seasonal changes, guiding the timing of planting and harvest. To Persian astronomers, it was one of the 4 royal stars, guardians of the heavens, each occupying a position in the sky like a sentinel. Its brilliance was not just light, it was authority, woven into the calendar and the rhythm of life. Rigel, the blue-white supergiant in Orion, told different stories. Its icy brilliance made it a marker for navigation. For Polynesian voyagers crossing the Pacific, Rigel was one of the key stars used to steer canoes across open ocean. Its place low on the horizon at certain times of year made it a dependable signpost, helping humans traverse vast distances long before compasses or maps. To them, Rigel was not a distant giant, but a companion, a steady guide across dangerous waters. The star's power was not abstract, it was survival. Even stars too faint to rival the Sun carried mythic significance when they stood out in their own way. The Pleiades, a cluster of hot young stars, appear as a tiny knot of brightness in the constellation Taurus. Though small compared to giants like Betelgeuse, they have been part of cultural stories across the world. The Greeks imagined them as the 7 daughters of Atlas, pursued into the sky. The Japanese called them Subaru, a word meaning unite, still remembered in the name of a car brand. The indigenous peoples of North America had their own stories, often connecting the cluster to lost children or guiding spirits. The star's beauty and compact brightness gave them meaning beyond their physical properties. The myths of giants often reflected their visible qualities. Red stars were seen as fiery, martial, associated with blood or war. Blue or white stars were cold, pure, often linked to guidance or gods of order. Brightness itself was seen as a sign of power. Stars that stood out were thought to influence fate, predict harvests, or mark the movements of gods. Where we see physics, ancient people saw intention. Their interpretations were not wrong so much as poetic, attempts to explain the awe they felt with the tools of story. What is striking is how many cultures, separated by oceans and continents, gave similar importance to the same stars. Antares in Scorpius, Betelgeuse in Orion, Sirius in Canis Major, all appear repeatedly in myths from different civilizations. These stars are not just bright, they are among the brightest in the sky. Their prominence made them universal touch points. Wherever people lived, they looked up, saw the same beacons, and wove them into their worldviews. In that way, the biggest stars in the universe have been shaping human thought for as long as stories have been told. Some myths even reflected the variability of these stars. Betelgeuse, for example, is a variable star, its brightness changing subtly over time. To astronomers today, this is evidence of pulsations in its bloated outer layers. But to ancient eyes, the change may have suggested a living presence, a star that waxed and waned like a breathing being. Such fluctuations could be interpreted as signs, moods, or portents. The cosmos was not static, but alive, responsive, filled with intention. Supernovae added to this perception. When a massive star dies in a brilliant explosion, it can appear suddenly in the night sky, brighter than any planet, sometimes even visible in daylight. Ancient Chinese astronomers recorded such events carefully, calling them guest stars. The supernova of 1054, which created the Crab Nebula, was documented across cultures, its sudden appearance startling and awe-inspiring. To those who saw it, the sky itself seemed to change overnight. A new star burned where none had been before. It was a clear sign, though what it meant was interpreted differently, an omen, a blessing, a warning. Today we see the Crab Nebula as a glowing remnant of a massive star's death. To ancient eyes, it was a miracle written in fire. The myths also reveal how deeply humans tied their lives to the rhythms of the sky. Stars were not just stories, but clocks and calendars. The rising of certain bright stars marked the beginning of seasons. In Egypt, the heliacal rising of Sirius, the moment it first became visible before dawn after being hidden by the sun's glare, coincided with the flooding of the Nile. This event was so crucial for agriculture that Sirius became central to Egyptian religion, associated with the goddess Isis, and celebrated in festivals. The star's brilliance in the sky directly shaped life on Earth. For the Navajo, the stars of Orion and surrounding constellations formed a sacred pattern used in storytelling and ceremony. For the Australian Aboriginal peoples, bright stars like Canopus and Betelgeuse were tied to ancestral beings and seasonal cycles. For the Norse, stars guided navigation across northern seas. Everywhere, the brightest stars were more than lights. They were anchors for meaning, woven into the fabric of culture. What makes this remarkable is that many of the stars central to ancient myth are the very ones we now recognise as giants: Betelgeuse, Rigel, Antares, Sirius. The qualities that made them mythically powerful are the same that make them astrophysically extraordinary. Their brightness, their colour, their variability, all stem from the physics of fusion and mass loss. Ancient people did not know about nuclear processes, but they saw the signs clearly. Their stories preserved what their senses told them, that some stars are not like the others, that some carry special power. Even today, the echoes of these myths remain. We name spacecraft after them, like the Subaru telescope, or draw inspiration for literature and art. The names of stars are reminders of the stories once told: Arabic, Greek, Latin, Sanskrit, and more, layered across centuries. Modern astronomy may have replaced myth with measurement, but the reverence remains. A star like Betelgeuse still inspires awe, not just for its scale, but for its role in human imagination. This connection between myth and science is not an accident. Both are ways of reaching for understanding, of grappling with things too large for daily experience. The ancients used stories, we use physics. But the impulse is the same, to explain the lights that shine above us, to place ourselves within the cosmos. When we talk about supergiants and hypergiants today, we are not so far from those early storytellers. We're still trying to comprehend the same brilliance, still finding meaning in the same stars. When you think of the universe, it's tempting to imagine that size has no end. Galaxies stretch across hundreds of thousands of light years. Black holes grow to billions of solar masses. Nebulae sprawl like ghostly veils too vast to comprehend. So why not stars too? If the universe allows for structures so immense, why can't stars keep growing, becoming endlessly larger and more luminous, giants without limit? The answer lies in the laws of physics themselves, which quietly but firmly draw boundaries around what stars can and cannot be. Stars form when clouds of gas collapse under gravity. The denser the region, the faster it falls inward, gathering more mass. At first glance, it might seem as though nothing should stop this process. Add more gas, make the star bigger, and the result should simply be a larger star. But there are counterforces, and they grow stronger the larger the star becomes. The first is radiation pressure, the outward push of light itself. Every photon carries momentum. As fusion in the core produces light, that light streams outward through the star's layers. The more massive the star, the hotter and denser its core, and the more photons are released. At a certain point, the pressure of those photons pushing outward begins to rival the inward pull of gravity. This balance is delicate. If gravity dominates, the star collapses further. If radiation dominates, the star begins to blow itself apart. The maximum size of a star is defined by this tug-of-war, known as the Eddington limit. The Eddington limit sets a theoretical cap on luminosity for a given mass. If a star shines too brightly, radiation pressure strips material from its surface, blowing away gas faster than it can be held in. It is as if the star's own light becomes a wind strong enough to erode itself. This process prevents stars from growing indefinitely. Observations suggest that stars more massive than about 150 to 200 solar masses cannot remain stable. Anything larger sheds material violently until it drops back under the threshold. In this way, the physics of light itself imposes a ceiling. Other processes reinforce this boundary. Fusion rates increase dramatically with mass, so the more material a star gathers, the faster it burns through its fuel. A star twice as massive as another does not simply shine twice as bright, it can shine tens or hundreds of times brighter. This runaway effect makes the larger stars unstable. Their cores burn furiously, their outer layers balloon outward, and their lifespans shrink to mere millions of years. Instead of growing endlessly, they grow quickly and die young. The faster they climb, the faster they fall. Rotation also sets limits. As stars form, they spin, and angular momentum resists collapse. For small stars, this spin is easily moderated, but for extremely massive stars, rapid rotation can fling material outward at the equator, creating disks of gas and preventing further growth. Some of the most massive stars known, such as those in the Tarantula Nebula, show evidence of such disks, signs that their own spin helps regulate their size. Even the environment matters. Massive stars form in clusters, where gas is shared among many newborn stars. As the most massive ignite, their radiation begins to disperse the cloud, blowing away material before other stars can grow too large. In effect, giants regulate not only themselves but also their neighbours, preventing unchecked growth across the cluster. This feedback keeps stellar masses within a range, ensuring that stars of thousands of solar masses never form, even if the raw material seems abundant. Despite these limits, the upper end of stellar size is still extraordinary. Stars like R136A1, possibly more than 200 solar masses at birth, stretch the boundary of what is possible, but even they cannot defy physics. Observations suggest that such stars lose enormous amounts of mass during their lifetimes, whittling themselves down as winds and eruptions carry material away. By the time they approach the end of their lives, they are lighter than they once were, their growth long since checked. Interestingly, the lower limit of stars is just as strict. Objects smaller than about 8% the mass of the Sun never reach the pressures needed to sustain hydrogen fusion. They become brown dwarfs, failed stars glowing faintly with leftover heat but never igniting fully. At the other extreme, objects larger than 200 solar masses cannot survive their own brilliance. Stars, then, occupy a narrow middle ground. Too small, and they never ignite. Too large, and they tear themselves apart. Infinity is denied at both ends. There is also the phenomenon of pair instability, which affects stars of particular mass ranges. When a supergiant becomes extremely hot, photons in its core can transform into particle-antiparticle pairs. This drains pressure from the radiation, causing the core to collapse suddenly. The collapse triggers explosive fusion, which can blow the star apart completely, leaving no remnant behind. This process is thought to occur in stars between about 140 and 260 solar masses. The very attempt to grow larger becomes a self-destructive instability. The laws of quantum mechanics themselves intervene to prevent infinity. The result of all these effects is a kind of natural self-regulation. The universe allows stars to grow big, but only so big. They can swell to thousands of times the Sun's radius, but only with relatively modest masses, as in red hypergiants. Or they can pack hundreds of solar masses, but only if they remain compact and luminous, like the blue giants of dense clusters. What they cannot do is be both infinitely wide and infinitely heavy. Something always gives way. This finitude is not a weakness, it is a strength. Without limits, the universe would look different. Infinite stars might dominate, consuming their neighbourhoods, preventing the delicate balance needed for galaxies to evolve. Instead, stars live within boundaries, and those boundaries create diversity. Red dwarfs, yellow suns, blue giants, red hypergiants. Each type exists because of the physics that prevents infinity. The cosmos is not a place of endless escalation, but of balance, of checks and counterweights, of harmony between opposing forces. When you think of a star like uyscuti, so swollen it could engulf Jupiter's orbit, it might feel infinite already. But even it is shaped by these limits. Its low mass compared to its radius shows the trade-off between size and density. It can expand only because its outer layers are thin, fragile, barely held by gravity. Push further, and those layers drift away, carried off into space. The limit is reached, and the star stabilizes within it. Likewise, the most massive stars we know shine with millions of times the sun's luminosity, but they cannot grow brighter without destabilizing. Their light peels them apart, their winds shred their atmospheres, their eruptions eject entire shells of gas. The limit is not a sharp line, but a balance point, one that stars circle around, sometimes pushing too far and being pulled back by their own instability. It is humbling to realise that even the giants of the universe cannot escape limits. For all their brilliance and size, they are bound by the same physics that binds everything else. Gravity, radiation, fusion, and quantum mechanics. These rules apply universally, from the smallest particles to the largest stars. There is no infinity in stars, only extremes within boundaries. And yet those boundaries do not make them less impressive. They make them more so. To exist at the very edge of what is possible, to burn so brightly that your own light tears you apart, to expand until your atmosphere drifts into space, to push against the limits of physics itself. This is what the giants of the universe do. They embody the tension between power and fragility, between expansion and collapse. Their lives are defined not by infinity, but by the drama of pushing against it. Every star that burns must one day come to an end. For small stars like red dwarfs, that end is gentle, a slow fading into cool embers over trillions of years. For stars like our Sun, the ending is more dramatic but still relatively calm, a swelling into a red giant, the shedding of outer layers into a planetary nebula, and the quiet collapse of the core into a white dwarf. But for the giants, for the massive stars that shine with millions of times the light of the sun, their deaths are anything but quiet. They end in explosions so violent they can be seen across galaxies. They end in supernovae. To understand why giants die so dramatically, we must look again at their hearts. In their final stages, supergiants fuse heavier and heavier elements, building layers like an onion. At the centre lies iron, and here the cycle stops. Unlike lighter elements, iron cannot release energy through fusion. Once a core of iron builds up, the star has reached a dead end. Fusion stops, but gravity does not. With no more outward pressure to balance it, the core collapses in on itself. This collapse happens in a heartbeat. In less than a second, the core implodes. Atoms are crushed. Electrons are forced into protons, creating neutrons and releasing a flood of neutrinos. The density rises to that of an atomic nucleus, unimaginable in human terms. Then, just as suddenly, the collapse rebounds. The outer layers, falling inward, crash against the dense new core and are hurled outward in a colossal shockwave. The star tears itself apart. The energy released is staggering. For a few days or weeks, a supernova can shine brighter than the entire galaxy that contains it. Billions of stars together cannot outshine this single event. The light is so intense that it can be visible even in the daytime sky. In 1054, when a star in our galaxy exploded, observers in China, Japan and the Middle East recorded a guest star so bright it could be seen for weeks in broad daylight. Today, we see its remnant as the Crab Nebula, a glowing cloud of gas expanding outward at thousands of kilometers per second. Supernovae are not just fireworks, they are creation events. In the heart of the explosion, temperatures soar high enough to forge elements heavier than iron. Gold, uranium, platinum, all are born in those violent seconds. The blast hurls them into space, scattering the seeds of future worlds. Every atom of gold in a wedding ring, every trace of iodine in a human body, every speck of silver in a mirror was once part of a star that died in a supernova. The death of giants makes life possible. The brilliance of a supernova is not uniform. Some are symmetrical, expanding outward evenly in all directions. Others are messy, with jets of gas shooting out faster in certain areas, leaving behind oddly shaped remnants. These differences depend on the size of the star, the speed of collapse, and the dynamics of the explosion. The result is always the same, though: a transformation. The star that once dominated its region is gone, replaced by a glowing nebula, a remnant core, and a shock wave moving outward into the galaxy. The remnants themselves can be just as extraordinary as the explosion. If the collapsing core is between about 1.4 and 3 times the mass of the Sun, it stabilizes as a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons. Some neutron stars rotate rapidly, emitting beams of radiation that sweep across space like lighthouse beacons. These are pulsars, spinning corpses of stars, broadcasting their presence with every turn. To astronomers, they are cosmic clocks, so precise they can be used to measure the fabric of space-time itself. If the core is even more massive, collapse continues. Nothing can stop it, not even the resistance of neutrons. The core shrinks past the point of no return and becomes a black hole. Here, gravity is so strong that not even light can escape. The star's death leaves behind not just a remnant, but a hole in space-time, an object that challenges our understanding of physics. From brilliance to darkness, the final curtain call of the biggest stars can end with the most mysterious objects in the cosmos. Supernovae also leave echoes in the galaxy. The expanding shock waves compress surrounding gas, triggering new waves of star formation. The heavy elements enrich nearby clouds, ensuring that the next generation of stars and planets is more complex than the last. This cycle is the heartbeat of galaxies, the rhythm of creation and destruction. Without the deaths of giants, the universe would remain simple, made only of hydrogen and helium. Their violent ends are what make complexity possible. For ancient observers, supernovae were both awe-inspiring and terrifying. A star that suddenly appeared where none had been before defied expectation. It was an omen, a miracle, a disruption of the cosmic order. Today we know the physics, but the awe remains. When modern astronomers witness a supernova in another galaxy, the feeling is much the same. A sudden, brilliant reminder of the power hidden in the universe. There are also different kinds of supernova. Type 2, supernovae are the classic deaths of massive stars collapsing under their own gravity. Type Ia supernovae, by contrast, are occur in binary systems, when a white dwarf steals material from a companion until it reaches a tipping point and explodes. Though different in origin, both produce blinding light and enrich the cosmos. The classification reminds us that even in endings, stars are diverse. The bigger stars may end in even rarer ways. Some undergo pair instability supernovae, in which their cores become so hot that photons transform into particle-antiparticle pairs, reducing pressure and causing a runaway collapse. The result is an explosion so complete that nothing remains, not even a neutron star or black hole. The star is entirely unmade, scattered into the galaxy. Such events are thought to be rare today, but may have been common in the early universe, when stars were more massive and less enriched with heavy elements. Even after the light fades, the legacy of a supernova endures. The Crab Nebula still glows nearly 1,000 years after its parent star exploded. Cassiopeia A, another remnant in our galaxy, continues to expand, its filaments of gas glowing with the energy of the blessed. These remnants are laboratories for astronomers, places where the physics of shock waves, magnetic fields, and particle acceleration can be studied. They are not just memorials, but active sites of science. From a safe distance, supernovae are beautiful. But if one occurred close to Earth, the consequences would be severe. A supernova within about 30 light-years could strip away Earth's ozone layer, exposing the surface to deadly ultraviolet radiation. Fortunately, no stars massive enough to explode are close enough to pose such a risk. Betelgeuse, though relatively near at 640 light-years, is far enough away that its eventual supernova will be a spectacle, not a catastrophe. Still, the idea that a star could suddenly light up the sky reminds us of how dynamic the cosmos truly is. The final curtain call of giants is not just about endings, it is about transformation. A star that once shone steadily for millions of years gives way to new structures, new elements, new possibilities. Its death is not silence but renewal. It is the handoff between generations, the way the universe writes continuity into destruction. And as we linger with this image of stars ending in brilliance, scattering themselves across galaxies, we can begin to think about what comes next. Not just in the immediate remnants, but in the long arc of cosmic history. Because these explosions do not only enrich the galaxy, they also contribute to the building blocks of life. They are the link between stars and biology, between astrophysics and ourselves. When a massive star dies, the explosion is only part of the story. What happens afterward, deep in the collapsed core, is just as important. The light of a supernova fades with time, the gas drifts outward into space, but the heart of the star does not simply vanish. Instead, it transforms into something new, something stranger, something that challenges the limits of our understanding. These are the children of collapse, neutron stars and black holes. A neutron star begins as the crushed remains of a stellar core. When the implosion of a dying star forces electrons into protons, neutrons are created. The result is an object so dense that the familiar structures of matter no longer exist. Atoms are gone. Nuclei are gone. What remains is a sea of neutrons packed shoulder to shoulder, squeezed into a sphere only about 20 kilometers wide. To imagine such density, picture compressing the entire mass of the Sun into a city-sized object. A teaspoon of neutron star material would weigh billions of tons, heavier than a mountain on Earth. The surface of a neutron star is no ordinary surface. Gravity there is so intense that if you were to drop something from just 1 meter above, it would strike the ground at a fraction of the speed of light, releasing more energy than a nuclear bomb. Nothing familiar survives at such scales. Atoms cannot exist under the pressure. Electrons are bound into neutrons, and even neutrons may be pressed into exotic states we do not yet fully understand. Some theories suggest that deep inside, matter may dissolve into a soup of quarks, the fundamental particles usually trapped inside protons and neutrons. If so, neutron stars may contain the densest, strangest matter in the universe. Despite their compactness, neutron stars are not lifeless husks. Many spin rapidly, remnants of the angular momentum from the original star. As they rotate, they produce magnetic fields far stronger than anything Earth could generate. In some cases, beams of radiation are funneled along the magnetic poles, sweeping across space as the star turns. To distant observers, these appear as regular pulses of light, as if the star itself were a cosmic lighthouse. These pulses can spin hundreds of times per second, their precision so reliable that they rival atomic clocks. Astronomers use them to test the very structure of space-time, to detect gravitational waves, to study the unseen fabric of the universe. Other neutron stars become magnetars, with magnetic fields so extreme that they distort atoms themselves. The fields are trillions of times stronger than Earth's, powerful enough to rip electrons from nuclei across vast distances. Magnetars occasionally release bursts of high-energy radiation, brief flashes that can outshine their host galaxies. These events remind us that even after death, stars can remain restless, still capable of sudden violence. If the collapsing core is even more massive, however, even neutrons cannot resist gravity. The implosion continues, crushing matter beyond the point of no return. At this moment, a black hole is born. A black hole is not just a dense object, it is a region of space-time where gravity is so strong that nothing, not even light, can escape. The boundary around it, the event horizon, marks the point of no return. Once crossed, all paths lead inward. The idea of black holes once seemed impossible, even absurd. How could something exist that traps light itself? Yet observations now leave little doubt. We see the effects of black holes on their surroundings. Stars whip around invisible centres, moving at incredible speeds. Gas swirls into accretion disks, heated until it glows with X-rays, before vanishing across the horizon. Entire galaxies shine with energy released by matter, falling into supermassive black holes at their cores. What begins as the death of a single star can grow into one of the most powerful engines in the universe. Stellar mass black holes formed from the collapse of giants usually weigh between a few and a few dozen solar masses. They are invisible directly, but their presence can be detected when they interact with companions. In binary systems, a black hole may strip material from a neighbouring star, creating an accretion disk that radiates intensely before disappearing into darkness. The signals from such systems are clear fingerprints of their existence. Perhaps most astonishing are the black holes detected through gravitational waves. When two black holes orbit one another and eventually merge, they release ripples in space-time itself. These ripples were predicted by Einstein a century ago, but only detected recently with observatories like LIGO and Virgo. The signals we capture on Earth are echoes of stellar deaths, vibrations from the final moments of massive stars that collapsed long ago. Listening to them is like hearing the universe remember its most violent events. Neutron stars too can merge, producing both gravitational waves and bursts of light. When they collide, they forge heavy elements in great quantities, spewing gold, platinum and other precious metals into space. Observations of these collisions confirm what theory long suggested, that much of the universe's heaviest elements are born not just in supernovae, but in the cataclysmic unions of collapsed stars. In this sense, the children of collapse are not just remnants, but creators in their own right, continuing the work of enrichment begun by their parent stars. It is easy to think of neutron stars and black holes as endings, but they are also beginnings. The neutron star is a laboratory of physics unreachable on Earth, a place where matter behaves in ways we cannot reproduce. A black hole is a gateway into the extremes of space-time, teaching us about gravity, relativity, and perhaps even quantum mechanics. Each one is a reminder that the death of a star does not erase its influence. It transforms it into something new, something that continues to shape the universe long after the original star is gone. These remnants also remind us of the balance between power and fragility. the same star that once blazed with unimaginable light collapses into an object that hides from view. The same core that once held fusion reactions becomes a silent neutron star or a devouring black hole. Power does not disappear, it changes form. The cycle of birth, brilliance, collapse and transformation continues, weaving itself into the fabric of galaxies. If we could stand safely near one of these remnants, the view would defy imagination. A neutron star would glow faintly, perhaps in X-rays, its surface smooth and hard like no rock we know. Its magnetic fields would distort your very atoms. A black hole would appear not as an object, but as a hole in the sky, warping light around it, bending the background stars into arcs and rings. The experience would be alien, disorienting, a reminder that the children of collapse are not just strange, they are unlike anything else in the cosmos. And yet, even as they feel alien, they are connected to us. The gold in jewellery, the platinum in electronics, the iodine in our bodies, all trace back to the deaths and collisions of these remnants. Our lives are written in their stories. We carry pieces of neutron stars and black holes in our chemistry, reminders that the universe is not separate from us, but within us. If collapse creates remnants of such strangeness, what do they mean for the larger picture of existence? How do they shape galaxies, influence the structure of the cosmos, and connect to the lives of countless other stars? Every ending in the universe carries with it the beginnings of something else. The death of a massive star may feel like destruction, but its legacy stretches far beyond the moment of collapse. A supergiant does not simply vanish when it explodes. Instead, it sends ripples outward, waves of energy and matter that continue to shape the cosmos for millions or even billions of years. These ripples become the seeds of new stars, new planets, and eventually new forms of life. The story begins with the material that a giant spends its life releasing. Long before its final explosion, a supergiant is already shedding pieces of itself into space. Its stellar winds carry carbon, oxygen, nitrogen, and other elements outward, forming shells and halos around it. These elements were forged in its core through fusion, transformed from simple hydrogen into complex building blocks. What begins as invisible gas eventually becomes the raw material for new worlds. When the star finally ends in a supernova, the process accelerates. The explosion hurls enormous amounts of enriched matter across space. Shock waves compress nearby clouds of gas, triggering them to collapse into new stars. The supernova becomes both a disperser and a catalyst, scattering elements and sparking the birth of future generations. It is an act of renewal written into destruction, a cosmic recycling process that ensures the universe does not stagnate but continues to evolve. We can see the results of this process in places like the Orion Nebula, where young stars are forming from clouds enriched by earlier generations of giants. The bright pillars and arcs of gas are not primordial material alone. They are infused with carbon from one star, oxygen from another, iron from a third. Each new star and planet inherits the chemistry of those that came before, carrying forward the legacy of ancient supergiants. In this way, the deaths of giants ripple through time, shaping not only the present but the far future. The very elements we depend on for life trace back to these cycles. The oxygen we breathe was fused in massive stars. The calcium in our bones, the iron in our blood, the carbon in our cells, all were created in stellar furnaces and scattered by stellar deaths. Even the water that fills oceans and rivers contains hydrogen from the dawn of the universe and oxygen from supernovae. Every drink of water, every breath of air, every heartbeat is connected to the lives and deaths of giants. The phrase, "we are stardust," is not a metaphor. It is literal truth. What is remarkable is how widespread these ripples are. A single supernova can scatter its material across dozens of light years. Over millions of years, that material mixes with interstellar gas, spreads across star-forming regions, and becomes part of countless systems. Your body contains atoms that were once inside different stars, possibly many of them. The universe is not only vast, it is interconnected, woven together by the sharing of matter across time and space. These ripples also shape galaxies on larger scales. Supernovae inject energy into the interstellar medium, stirring it, preventing gas from collapsing too quickly. This feedback regulates star formation, ensuring galaxies evolve steadily rather than consuming their gas in a single burst. Without the disruptive influence of massive stars, galaxies might form stars too quickly, burning out early and leaving behind little material for later generations. Giants impose a rhythm, a balance, ensuring that creation is stretched across cosmic time. Astronomers sometimes call this process galactic ecology. Just as ecosystems on Earth recycle nutrients through cycles of birth, growth, decay, and renewal, galaxies recycle matter through stars. Supergiants are the apex contributors, the ones that return the richest material. Their ripples are not confined to a single place or moment. They propagate, mixing and spreading, ensuring that complexity increases with each cycle. The planets and people of today are built from the ashes of long-dead stars, and those in turn will someday be recycled again. This recycling is not uniform. Some regions of galaxies are enriched more quickly than others, depending on where giants lived and died. Spiral arms, where stars are born in abundance, become chemical laboratories, filled with heavier elements from multiple generations of supernova. The outskirts of galaxies, where stars form more slowly, may remain poorer in heavy elements for billions of years. This uneven distribution explains why some planetary systems are rich in rocky worlds while others may lack them. The presence of planets like Earth is not random. It is tied to the ripples of giants that seeded our part of the galaxy long ago. We can even look into the night sky and see these ripples preserved. The Crab Nebula, the Veil Nebula, Cassiopeia A, all are remnants of supernovae, glowing with the light of matter flung outward centuries or millennia ago. These clouds are not just beautiful, they are the seeds of the future, raw material waiting to join the next cycle of star formation. When you look at such a nebula, you're seeing the ripples of giants still moving outward, still shaping the future long after the star itself has gone. The ripples extend into the deepest aspects of existence. Even the possibility of life depends on them. Without carbon, there can be no complex chemistry. Without oxygen, there can be no water. Without iron, planets cannot form solid cores to generate magnetic fields. These elements are not optional, they are essential, and all of them come from giants. The very fact that the Earth exists, with its oceans and atmosphere and biosphere, is a direct consequence of supergiants that lived and died billions of years before the Sun was born. Thinking of this can reshape the way we see ourselves. It is easy to imagine life as small, isolated, confined to a tiny planet in a vast universe. But in truth, life is the continuation of a cosmic process billions of years in the making. The atoms in your body are older than Earth itself, forged in the furnaces of stars long gone. When you breathe, when you move, when you think, you're carrying forward the ripples of giants. Their legacy is written in you. The phrase ripples through time captures this continuity. A ripple begins small, a disturbance in one place, but it spreads outward, affecting everything it touches. A supergiant's death is one ripple, but across millions of years and thousands of light years, it becomes part of countless worlds. The effect is not immediate but cumulative, layering generation upon generation. The ripples of stars that lived in the early universe are still present now, inside us, inside Earth, inside every living thing. Even now, new ripples are being created. Massive stars in the Tarantula Nebula, in the Carina Nebula, and in distant galaxies are fusing elements that will one day become part of future worlds. Their deaths will scatter those elements, continuing the cycle. The story is not finished. it is ongoing. The universe is still making the building blocks of life, still spreading ripples outward. Somewhere, billions of years from now, beings may exist who carry the atoms of stars that are shining today. Astronomers track this enrichment by measuring the metallicity of stars, the fraction of their mass made of elements heavier than helium. Older stars born early in the universe have low metallicity. Younger stars, like the Sun, have more. Each generation increases the abundance of heavy elements. This is how we know the process is cumulative, that the ripples continue to build. It is also how we understand our own origins. Earth could not have formed early in the universe. The elements it required did not yet exist in sufficient abundance. Only after billions of years of giants living and dying did the galaxy contain enough carbon, oxygen, silicon and iron to make planets like ours. So when we think of supergiants, it is not only their brilliance, their winds, or their violent deaths that matter. It is their role as givers, as seeders of worlds. Their lives ripple outward through time, connecting past, present and future. Without them, there would be no planets, no oceans, no living beings to wonder at the stars. The ripples of giants are the foundation of everything. And as we hold this thought, as we let the image of ripples spreading across galaxies settle in mind, we can begin to reflect on perspective. Because if giants seed the cosmos with their deaths, what does that mean for our own sun? How does our modest star compare to these titans, and what role will it play in the great cycle? When you stand under the sky on a clear day, it is easy to take the sun for granted. Its light fills the world so completely that it feels ordinary. It rises every morning, it warms the air, it powers the rhythms of plants and seasons. It seems steady, modest, perhaps even unremarkable compared to the great stars that populate astronomy books and photographs. After all, Betelgeuse could swallow our sun whole and still have room left over. Rigel outshines it by tens of thousands of times. Uyscuti stretches so far that if it sat where the sun does, its edge would reach far beyond Jupiter's orbit. Against such giants, our star can appear small, and yet, when you place the sun in its proper perspective, what emerges is not weakness or insignificance, but a kind of quiet perfection. The sun is what astronomers call a G-type main sequence star, a yellow dwarf. It is not the largest, nor the hottest, nor the most luminous. In fact, by cosmic standards, it is average. Most stars in the Milky Way are smaller and cooler red dwarfs, barely glowing compared to the sun. A smaller fraction are larger and more powerful. The sun sits in the middle, balanced between extremes. That balance is exactly what makes it special. Consider its size. At about 1.4 million kilometres across, it is huge compared to Earth, more than 100 times wider, but compared to a supergiant, it is tiny. Yet this modest size means it burns its fuel slowly, stretching its life across billions of years. Giants, with their swollen forms, blaze quickly and die young. The sun's ordinariness gives it longevity. It has already shone for 4.6 billion years and will continue for another 5 billion or so. That time span is what allowed Earth to form, oceans to gather, life to emerge, and civilizations to rise. Had we orbited a giant, there would not have been enough time. Its luminosity is another measure of this balance. The sun radiates steadily, neither too faint nor too blinding. The habitable zone it creates is positioned perfectly for Earth, where liquid water can exist. Around a giant, the habitable zone would be far out, shifting with the star's instability, making conditions unpredictable. Around a dwarf, the habitable zone would be so close that planets would likely be tidally locked, with one side scorched and the other frozen. The sun sits in the middle ground, bright enough to sustain warmth, stable enough to preserve balance. Even its variability is restrained. All stars fluctuate in brightness to some degree. Giants can pulsate wildly, dimming and brightening by noticeable amounts over months or years. The sun, too, has cycles, most famously the 11-year solar cycle of magnetic activity. But these fluctuations are small compared to its total output. For life on Earth, that steadiness is critical. A sun that flared too violently or dimmed too drastically would make climates unstable. The relative calm of our star is the reason complex ecosystems can persist over millions of years. In terms of chemical enrichment, the Sun is also well placed. It was born at the right time in galactic history, after enough generations of giants had lived and died to seed the galaxy with heavy elements. That is why Earth contains the metals, silicates, and carbon compounds needed for life. Earlier stars lacked those resources. Later stars may form in more enriched environments, but our Sun struck the balance, arriving when enough building blocks existed, but before the galaxy exhausted its gas. When you compare the Sun to the giants, the contrast reveals the importance of ordinariness. Giants dominate their neighbourhoods with light and winds, but they vanish quickly, leaving chaos behind. The Sun, modest and steady, nurtures instead. It is not a destroyer, but a caretaker. Its power is sufficient to warm and illuminate, but not so overwhelming that it scours. It is, in a sense, precisely what a planet like Earth requires. From another perspective, the Sun is not ordinary at all. For humans, it is the most important star in the universe, the one we live under, the one we depend on. Every breath of air, every meal, every drop of rain is powered by it. Photosynthesis turns sunlight into food. Weather patterns are driven by its warmth. Tides may be influenced by the moon, but the energy of motion, growth and climate all come ultimately from the Sun. To us it is not one star among billions. It is central, vital, defining. The cosmic perspective asks us to hold both truths at once. The Sun is ordinary, one of hundreds of billions, modest compared to giants, and the Sun is extraordinary, the single star whose light makes our existence possible. In its balance lies its greatness. Its ordinariness is its perfection. If you could travel across the galaxy and look back at our solar system from afar, the Sun would appear as a faint point among countless others. It would not stand out. Yet if you could trace the chemistry of the planets around it, you would see something remarkable. You would find water, oxygen, carbon compounds, and life itself. You would realise that in its quiet way this modest star gave rise to something giants never could. The giants burned too hot, lived too briefly, destabilised too much. The Sun nurtures. In the balance between size and stability, it makes possible the fragile miracle of life. Astronomers often remind us that most stars in the universe are smaller than the Sun. Red dwarfs are the majority, making up perhaps 70% of the Milky Way's population. These stars are incredibly long-lived, stable for trillions of years. If life is to arise elsewhere, red dwarfs may provide many opportunities, but their habitable zones are narrow and close in, vulnerable to stellar flares. The Sun may be rarer, but it offers broader, gentler conditions. It sits in a sweet spot, a compromise between abundance and suitability. Comparisons also highlight how perception shapes meaning. When we gaze at Betelgeuse or Rigel, they inspire awe by their sheer brightness or size. But when astronomers study exoplanets, they often search around stars like the Sun. The giants impress the eye. The modest stars enable the possibility of life. In that sense, the giants are spectacles, but the Sun is a foundation. Both matter, but in different ways. The perspective extends even further when you consider time. The giants come and go in millions of years, brief candles in cosmic history. The Sun's lifetime stretches into billions, a scale long enough to encompass the entire story of Earth's biosphere. Life had time to crawl from the oceans, evolve into forests, spread into countless forms, and eventually become beings who could look back at the sky. None of this would have been possible under the watch of a giant. Time itself is the gift of the Sun's modesty. When we place the Sun among the giants, then, the message is not one of inadequacy. It is one of gratitude. We do not need a star that can engulf planets or outshine galaxies. We need one that is steady, balanced, and long-lived. In its quiet way, the sun is more powerful for life than any giant could be. Its ordinariness is the condition for our existence. And yet, reflecting on this perspective also makes the giants no less fascinating. Their brilliance, their wins, their deaths enrich the universe in ways the sun alone cannot. Without them, the elements of Earth would not exist. Without them, the sun would not have had the resources to form a rocky planet like ours. The giants and the dwarfs, the spectacular and the modest, all play their roles in the cosmic drama. Each is powerful in its own way. So when we think of the sun among the giants, we can hold two thoughts together: that the giants are more luminous, more massive, more dramatic, and that the sun, precisely by not being those things, sustains us. Power comes in different forms. The giants shape galaxies, the sun shapes life. Both are essential. As we rest with this balance, we can also notice how easily perspective shifts. From Earth, the sun dominates our sky. From across the galaxy, it would vanish into the crowd. From the perspective of physics, it is ordinary. From the perspective of biology, it is everything. This play of scales, of contexts, is what gives the cosmos its richness. The giants do not diminish the sun, they highlight its quiet perfection. When you gaze at the night sky, every star looks the same size. Each one is a pinpoint of light, no larger than the head of a pin held at arm's length. The brightest may twinkle more, the faintest may seem barely there, but all share the same essential appearance. You cannot tell which are near and which are far, which are small and which are vast. Perspective flattens them, turning the three-dimensional universe into a simple dome overhead. And that illusion is one of the reasons our awe is sometimes misplaced. If you compare Betelgeuse to the sun on paper, the difference is staggering. Betelgeuse is about 1,000 times larger in diameter, so wide that it could engulf Earth's orbit entirely. If you set the two side by side, the sun would look like a grain of sand against a beach ball. And yet, when you look up at the sky, Betelgeuse is just another dot, barely brighter than its neighbours in Orion. Its true enormity is hidden by distance. The same illusion applies to all giants. Rigel shines brilliantly to us not because it is the biggest, but because its distance and luminosity combine in just the right way. Uyscuti, larger than them all, is invisible without a telescope, tucked away in a dusty region of the Milky Way. The giants are everywhere, but our eyes cannot reveal them. The sun presents the opposite illusion. It looks massive in the sky, filling our vision, dominating our days. You can feel its heat on your skin, see the shadows it casts, and rely on it for every part of your life. But in truth, it is modest, smaller than most stars visible in the night sky. Its apparent size comes not from its greatness, but from its closeness. The sun is our neighbour, only 8 light minutes away. That intimacy makes it seem far larger than it is. If it were as distant as Rigel or Betelgeuse, it would vanish into faintness. This contrast between appearance and reality is what makes perspective tricky. Our senses evolved to judge distances and sizes on human scales. Mountains, rivers, trees, animals. We are good at estimating whether something is close or far in a familiar landscape. But space operates on scales so vast that our instincts fail. Stars become points. Distances become meaningless. Sizes become illusions. What feels huge may be small. What feels faint may be immense. The universe deceives us by compressing its grandeur into pinpricks of light. Astronomers overcome this illusion with tools. They measure distances through parallax, watching how a star shifts against the background as Earth orbits the Sun. They calculate luminosity from spectra, disentangling the effects of distance from the true brightness. They compare colours to temperatures, linking what we see to the physics beneath. These techniques reveal what our eyes cannot. that the night sky is not flat but layered with depth, not uniform but filled with extremes. Betelgeuse, Rigel, Antares, and countless others stand revealed as giants, while nearby red dwarfs, though invisible to the eye, dominate by sheer numbers. The illusion gives way to reality, but the reality is even more astonishing. The illusion of size also shapes culture. Ancient people named constellations by connecting the dots they could see, not by the physical realities behind them. Orion looks like a hunter only because the stars appear close together from Earth. In truth, they are scattered across hundreds of light years. Betelgeuse, Rigel, Bellatrix and Saiph are not neighbours but strangers, aligned only from our perspective. The patterns are illusions, useful for storytelling and navigation, but not reflective of the stars' actual relationships. What feels connected is not. What feels random may be linked by invisible forces. Even planets play tricks with perspective. Venus can outshine every star in the night sky, but it is small, merely reflecting sunlight. Jupiter, though massive, appears as a bright dot no different from the stars unless you use a telescope. The illusion lies in brightness, in apparent size, in the way distance disguises scale. A giant galaxy millions of light years away may look fainter than a star in our own neighbourhood. The true hierarchy of the universe is hidden, leaving us with impressions that must be corrected by knowledge. But the illusion is not simply a mistake, it is part of the wonder. The fact that all stars look alike to the naked eye places them on equal footing, inviting us to wonder what lies beyond the uniformity. It forces us to ask questions, to measure, to imagine. Without the illusion, perhaps our curiosity would not have been stirred as strongly. The mystery of the night sky lies in its simplicity as much as in its complexity. It looks flat, but it is deep. It looks uniform, but it is varied. It looks small, but it is immense. The warping of awe also reveals something about human perception. We are drawn to what is bright and visible, often overlooking what is hidden. Sirius, the brightest star in our sky, is not the most powerful or the largest, but it captures attention because of its prominence. Giants like uyscuti, invisible to the eye, inspire awe only once we learn about them. Knowledge reshapes awe, turning faint points into titans in our minds. Perspective is not just about what we see, but about what we understand. In this way, science deepens rather than diminishes wonder. Learning that Betelgeuse is vast beyond comprehension, that Rigel blazes with tens of thousands of solar luminosities, that uyscuti could engulf Jupiter's orbit, these facts make the illusion more meaningful. The small dots become symbols of immensity. The faint glimmers become echoes of power. Awe shifts from the visible to the invisible, from what appears large to what truly is. It is humbling to realize that the illusions of size apply even beyond stars. Galaxies too play tricks. The Andromeda galaxy appears as a faint smudge in the sky, something you could mistake for a cloud. Yet it contains 1 trillion stars, more than the Milky Way. Quasars, some of the brightest objects in the universe, appear only as faint specks in telescopes, their true brilliance hidden by distance. The universe consistently disguises its greatest extremes, presenting them as subtle hints. The awe lies not in the first impression, but in the revelation behind it. The illusion also works in reverse. The moon appears enormous in the sky, large enough to dominate the horizon. But compared to Earth, it is small, barely 1/4 of its diameter. Its closeness exaggerates its presence just as the sun's does. This combination of nearness and brightness shapes our perception, making small things seem vast, making vast things seem small. Our awe is warped not because the universe is misleading, but because our senses are tuned to smaller scales. And yet, perhaps this is not a flaw, but a gift. If we could see the night sky as it truly is, with accurate sizes and distances, it might overwhelm us. The immensity might feel too large, too impersonal. The illusion makes it approachable. something we can connect with, even if imperfectly. We see dots, we make patterns, we tell stories. Then, as our understanding grows, we peel back the illusion and find the reality even richer. Awe comes first from simplicity, then from complexity. Reflecting on this illusion invites us to be cautious about appearances in all things. The brightest is not always the most powerful, the nearest is not always the largest, the familiar is not always the most important. Perspective can mislead, but it can also inspire curiosity. The night sky is a lesson in humility, reminding us that our senses are limited, our view partial, our impressions incomplete. To see truly, we must look deeper, measure carefully, and let knowledge reshape what awe means. And as we rest with this thought, we can allow the illusion itself to soften into comfort. It does not matter that we cannot see uyscuti with our eyes. It does not matter that Betelgeuse looks like just another dot. What matters is that the light has travelled across space to reach us, carrying the stories of giants, even if disguised. Our awe may be warped, but it is still real. And in that awe, we find connection. From here, the thought naturally extends to reflection. The night sky is not only about measurement and illusion, but about experience. For as long as humans have lived, stars have been companions in darkness, lights that soothe and inspire. They are not just objects of science, but sources of comfort, reminders of our place in something larger. And as the giants remind us of scale, the act of looking up reminds us of rest, of stillness, of the quiet continuity of the cosmos. As the story of the giant settles in your mind, you may find yourself drifting back to the simple act of looking up at the night sky. For all the numbers, the physics, the scales and the measurements, what matters most in the end is the quiet feeling of being under the stars. You do not need to know which is Betelgeuse, which is Rigel, which is Antares, or where uyscuti hides behind clouds of dust. It is enough to know that they are there, scattered across the galaxy, glowing steadily, sending their light across time and distance to find you here. Imagine yourself lying somewhere dark and still, far from city lights. The air is cool, the ground steady beneath you. Above, the stars are scattered like seeds across a deep canvas of black. Some shine faintly, some burn bright, and though each one looks small, you now carry the knowledge of their true power. You know that some are giants, swollen to sizes beyond comprehension. You know that their light has taken centuries, even millennia, to reach you. You know that their brilliance comes at the cost of short, intense lives. And yet, none of that diminishes their beauty. If anything, it makes their quiet presence more meaningful. As you breathe slowly, you might picture one of those giants, maybe Betelgeuse with its soft red glow, or Rigel with its icy light, or even uyscuti, invisible to the naked eye but present nonetheless. Imagine what it would feel like to see the world lit by such a star, its vast disk filling the sky, its light painting everything in hues unfamiliar to us. Then remember that you are safe here, at just the right distance from a modest sun, watching from afar. The giants burn out there and you rest here, their light a visitor but not a danger. The stars ask nothing from you. They do not rush you. They do not demand that you measure or calculate. They simply shine. Their light enters your eyes, quiet and steady, a connection across impossible gulfs. In that light you can let your thoughts wander, not as equations or data, but as feelings. The universe is immense and you are small within it, but not separate. The atoms that make you once belonged to stars carried here by winds and supernovae, scattered and gathered, recycled across billions of years. You're not an outsider looking in. You're part of the same story. Think of how long those journeys have been. The light from Betelgeuse arriving now left the star more than 6 centuries ago, long before telescopes, long before electricity, long before the world we know today. The light from Rigel began its journey even earlier. The light from uyscuti started when human history itself was still young. To look at the stars is to look back in time, to receive messages from eras long past. And now, as those photons touch your eyes, they become part of your story too, threads woven into your memories of this night. There is comfort in that. The universe can feel overwhelming, but it can also feel gentle. The stars are not rushing. Their processes take millions or billions of years. Their distances soften their power. Their light arrives quietly, like whispers across space. You can rest knowing that nothing in the sky is hurried. You can take your time as the universe takes its time. You're not out of step. You're moving at the right pace. The giants themselves may live quickly by cosmic standards, but even their millions of years dwarf human lifetimes. When Betelgeuse eventually explodes, it will be a spectacle, but until then it shines as it has for generations. When uyscuti collapses, its light will blaze, but for now it is steady, invisible without aid, but still there. These stars remind us that change comes slowly, that vast processes unfold gradually, almost imperceptibly. As you lie beneath their light, you can let go of urgency. There is no rush. The stars will keep shining. The knowledge of their power does not need to keep you awake. Instead, it can be a lullaby. The idea that something so large, so powerful, so far beyond comprehension, can exist quietly above you is reassuring. The universe is not fragile. It endures. Its structures are immense. Its processes steady. You are small within it, but you are also safe within it. The stars have burned for billions of years, and they will continue long after you close your eyes tonight. If your thoughts drift, let them drift with the stars. Imagine their winds carrying gas outward into space, breathing across light years. Imagine their explosions, scattering elements into nebulae that glow like cosmic gardens. Imagine the new stars forming in those clouds, the new planets coalescing, the cycles continuing endlessly. Then bring your attention back to your own breath, rising and falling, your own steady rhythm mirroring the slow rhythms of the stars. You're in sync with the cosmos, not apart from it. The illusion of size that once tricked your eyes into seeing all stars as points can now serve as a comfort too. You do not need to grasp their full scale. You can simply let them be dots in the sky, lights to watch as your thoughts soften. Behind each dot lies a story of fusion, winds, collapse and rebirth. But you don't need to hold all of that now. You can just let them be, and let yourself be, without effort. Perhaps you can imagine falling asleep under the light of one of those giants. Not literally, but in thought. You might picture yourself on a quiet plain, the sky filled by a swollen red star, its glow casting everything in soft, strange colours. Or perhaps you imagine a blue-white giant, its light cool and serene, spreading across a horizon. In your imagination, you can rest beneath their brilliance without fear, their power turned gentle by distance and thought. In this way, the stars can become companions in sleep, guardians of rest. The truth is that you already sleep under their light. The stars above you now are shining as you lie here, whether you see them or not. Their photons fall across Earth constantly, faint but steady, mixed into the background of night. You are already bathed in their glow, already part of their story. To fall asleep under the light of a distant giant is not imagination alone, it is reality. As your eyes grow heavier, you may let the details of fusion and collapse fade into the background. You do not need to remember the names or the numbers. All that matters is the feeling, that the universe is vast, that it has been here long before you, that it will be here long after you, and that in the middle of it, you have a place. You're made of the same matter as the stars, carried forward in their ripples, resting now in their quiet light. And if sleep comes, let it come easily. The stars will keep shining. The giants will keep burning until their time comes. Their light will continue to cross space, arriving steadily, softly, carrying their stories through time. You do not need to hold it all. You can let it go, knowing that it is still there, steady above you. The universe does not vanish when you close your eyes. It waits, patient and calm, its rhythms steady, its stars eternal in their scales. So rest now, as though you were lying beneath the light of a giant, its glow softened by distance, its power turned into comfort. Rest knowing that you are part of the same story, that the atoms in your body once shone in stars, that the breath you take is tied to cycles stretching across billions of years. Rest under the stars as countless others have done, letting their light be a companion, a guide, a gentle reminder of continuity. And as your thoughts drift further, as they soften into dreams, remember only this: the giants are out there, immense and powerful, yet their light finds you here, quietly, gently, enough to carry you into sleep. Thank you for spending this time under the stars with me. If you found peace in this journey through the lives of giants, know that there are always more stories in the cosmos waiting to be told. You can return here whenever you'd like, to rest, to wonder, or simply to let the rhythm of the universe carry you towards sleep. If this brought you comfort, I invite you to support this space by liking the video, subscribing to the channel, or sharing it with someone who might also enjoy drifting into rest with science as a companion. Your presence here matters, and it helps keep these explorations alive. For now, close your eyes, let the stars fade gently in your thoughts, and rest in the quiet knowledge that you are part of something vast and beautiful. Until next time, may your dreams be as calm as the night sky, and may the universe keep you company as you sleep.